a Hamiltonian, and so on. Today, various new hardware architectures are being developed for implementing these quantum programs on a real hardware. The most common way to program Oh, okay. Hi, is this better? Yeah. Okay. So others like Tower and Spire can kind of provide you features like that are very familiar to programming language people, like control flow in quantum programming. And others like SilQ can kind of provide you features for both. Overall, these languages make programming easier and way more scalable, but they come with their own drawbacks. Their modular abstractions can sometimes lead to inefficient circuit design. That's where Spare comes in. It's a tool for compiler-generated circuits and leverages the abstractions present in these languages to optimize these circuits further. So let's walk through two language examples to see what we'll be dealing with in this presentation. First, we have uncomp. It's a more circuit-level-like language, which can be used to describe quantum programs. And we have an example of an adder operation here and the corresponding circuit on the right for n equals to 2. Starting off, uncomp allows you to have different types of qubits. You can have data qubits that start and end in an unknown quantum state because they're basically storing the variables of the program. And others are ancilla qubits. They start and end in a known quantum state, most frequently the 0 state, so they can be used to store temporary variables, just to make your computation more efficient and easier to perform in the restricted resources we have. In uncomp, programmer manually writes out parts of the circuit, like the compute gates, that store some temporary result on your ancillas, and the transform gates that use those temporary results to change the quantum state around. Now, unlike a classical program, you can't just get rid of those temporary results that you created. What you need to do is you need to carefully unentangle them from the rest of the qubits, and one way to do that is uncomputation. Uncomp allows you features to just call circuit with uncomputation, where the compiler would go in and directly instantiate and synthesize these uncompute gates for you, creating this compute transform uncompute pattern. Now we can look at circuits from control flow languages as well. Tower is one such language. It basically allows you to write code that looks like classical code, but deals with quantum variables. And we can compile this to a circuit with compilers like Spire, which is particularly focused on Tower. In this compilation process, control statements basically become controls on your quantum circuit. And any temporary variable assignment can be handled by the with block, which allows you to instantiate temporary results, which are used inside the do block for your computation, and then undone. Just for explicitness, I've added the undo block there. And you can pattern match what block corresponds to which part of the circuit here. So this is the same pattern we saw in uncomp as well. We call it compute transform uncompute, or CTU for short. One thing we note is that the compiled circuit is sometimes very inefficient, and you can see that by just taking the Tower circuit we were seeing and like a more efficient implementation just on the right, which can be done by just very simple rewrites. So one thing we do note there is, luckily, these compiled circuits have a lot of features that can be exploited for optimization. First of all, they have these repeated CTU patterns that come up multiple times in the circuit. And they have a lot of qubits that are either ancillas. They start and end in a known quantum state, like the state 0, shown highlighted here in yellow, or output qubits, which start off as an ancilla, but they're not uncomputed, so they're unknown at the end. So those are highlighted all in yellow for all the regions that are subsetted to a known quantum state. We build optimization tools by basically building rewrites that leverage these two pieces of information to optimize circuits like these. We'll work with the adder circuit example that we wanted to, and we'll extract the CTU pattern out of it. You have the compute gates here on the left and the uncompute gates on the right. The corresponding pairs match each other in color, so you can see that. And the transform gate is right here in the middle. Starting off, we see that the compute gates compute some result, uncompute gates undo that result, but the temporary gate right there in the transform gate right there in the middle uses that result during the course of the circuit. Thus, it creates a dependency between the compute-uncompute pair. One way to resolve that dependency is to check all the possible cases for which the transform gate can be applied. This can be done by just taking a qubit that it is not active on, that is operated on by the uncompute gates, and simply enumerating the two possible cases. You can have 0 and 1. I can keep doing, and these gates have mutually exclusive controls, so only one of them will be applied, given a quantum state for A0. And you can keep doing that to end up in a 2 to the power n replicates if you expand onto n qubits. Once you've done this, I promise you, you can move the compute gates all the way to uncompute gates, which allows you to go further in your optimization process. The way this works is there are a bunch of cases where control conditions don't match, which means they're applied mutually exclusively on the circuit and can simply be swapped. And you can keep doing that until you end up in a scenario where control conditions of the compute gate are a strict subset of your replicate. Now, you can still perform the swap, but you need to preserve the action of the compute gate on its target, which can be done by simply just swapping the control around, in this case, because it's just an X gate. And I can keep doing that until all the way till I have my compute-uncompute pair near each other. I can do the same thing for the other compute gate, changing 2 replicates in the process, getting this circuit here. Now, once these swaps are done, I can merge these compute-uncompute gates together, resulting in a circuit with just the replicates. To further optimize this circuit, we find that there are a lot of cases where we are just enumerating the same gate for 2 possible control conditions. I can merge them back in an action sort of inverse of the expansion that we saw earlier, and get a circuit which just skips that control. You can keep doing that further until we end up in this circuit which just has multiple mismatches. Now, moving on, with all the basic rewrites we've discussed up till now, right here on the left, we can't actually optimize that circuit further. One thing we can do is combine them together to build larger circuit transforms that can allow you to move forward in the optimization process. One way that works is, in the case of these multiple mismatches, we can convert them into a new CTU pattern in the circuit by just adding and deleting some gates and using the basic rewrites we had right now. We can keep doing that further, and we have now a circuit with 2 CTU pairs. Nicely enough, using all the basic rewrites, we can merge CTU patterns together as well, resulting in a circuit which just has 1 CTU pattern that's hopefully better than the one you started off with for optimization. These 2 circuit transforms that we just discussed generate new CTU patterns that can then be leveraged later on during the compilation process for further optimization as well, once you see all other targets. These rewrites are correct, and the way to check the correctness of these rewrites is to just check the unitary applied by the original and the transformed circuit, and if the difference between those unitaries is simply 0, equality is preserved. This is a standard definition you guys might have seen before, and it just means that the circuit is equal for all input states for all qubits. One thing that doesn't catch is ancillas. Ancillas are kind of special. They are restricted to a special state, the 0 state, on its interface. And starting with the circuit with the multiple mismatches, you can see that there are a bunch of cases where control conditions are never satisfied, like control on state 1, and the highlighted portion is all restricted to state 0, and trivial controls that are on state 0. That results in a final circuit that has just 1 Toffoli gate, which is this rewrite is only correct assuming ancillas are correctly used. This means that we can now formalize this equality for these kind of rewrites as this type 2 equality right here, where if qubit I is subsetted to 0 state in this ket notation, and the delta U admits this bracket term, we don't need to get into the details of what this means right now, but just mean that the difference between the unitaries only shows up if qubit I was in 1 state, which is just not possible if it was correctly initialized. Moving on, we can walk through one simple proof. We have the gate deletion rewrite that deletes this gate if it was controlled on state 1, and it's subsetted to state 0 on its interface. And here's the unitary shown here on the right in tensor product notation. The only reason we want this notation is that it's pretty easy to make it symbolic and extendable, where each control becomes its own bracket term. And you can then club terms together, show final unitary. And since this just deletes the gate entirely, the transformed unitary is simply identity. And the difference matches the type 2 definition that we started with. For more details, please just look in the paper of how this rewrite is proven, and all others are proven as well. This is the overall flow that we're working with. We can now move on to our compiler implementation that does this optimization called SPARE. SPARE takes compiler-generated circuits from Spire, which is the compiler for Tower, and uncomp-generated circuits. And the way it works, it first comes with custom frontends that modifies the the circuit from these languages to be lowered only onto the SPARE IR. And it tracks the ancilla information from the original circuit to correctly annotate the SPARE IR at the interfaces to know which things are ancillas where. which you can then use to basically have your circuit in the spare IR, which has multi-controlled single target gates. And we use ancilla state propagation to just sort of push that information where the qubit is restricted to special states around. The rewriter comes with various optimizations, like it applies those rewrites speculatively. It caches the CTU targets it has already seen. It applies the full expansion to 2 to the power n replicates for only smaller CTU pairs, which span fewer qubits, and uses a more direct optimized rewrite flow for larger CTU patterns. And it comes with various popular lowering optimizations that previously people have worked on when it comes to uncomputation as well. So if we evaluated spare on these tower and uncomp generated circuits, range spanning a few qubits to hundreds of qubits, and circuits which span from tens of gates to thousands of gates, and in some of our ablation studies, tens of thousands of gates as well. We optimize these circuits for across these 4 metrics, for qubit count, 2-qubit gate count, etc. And we just report our numbers in the next slide in this percentage improvement formula. Don't need to get into the details, it's just like, what is the percentage improvement relative to the original implementation? We compare against various other circuit optimization tools that are out there. And we find that spare generally improves upon all metrics for all the benchmarks we were evaluating for. These are just a subset from the paper here. And there are more in the paper. You see all the negative percentage changes is just like how much what percentage amount we were able to reduce the original circuit. And there are some cases where we are slightly worse on one of the metrics to get an overall improvement on all the others. In comparison, we find that other circuit optimization tools are generally much worse. For example, Quartz can't even scale to the larger scale problems we are dealing with. And others like Feynman and PyZX are often limited by the fact that they can't deal with the lowering optimizations that these compilers often use, and hence are sometimes limited on what kinds of optimizations they can use, and are not aware of these structures anyway in comparison to spare. Here, just like the average numbers, I've reported it out there just to see what that reduction looks like. Stepping back, one thing we wanted to check, though, from this overall work was, could we just not have implemented these rewrites as a higher-level program transformation? What's the difference between those two? One thing we found is that these gate-level rewrites, in some cases, yes, do have corollaries to higher-level program transformations. Some, like the ancilla state propagation that we were doing to annotate the ancilla qubits around, is basically similar to constant propagation in a compiler. Or the single mismatch merge that we were doing, which merges gates and deletes a couple of controls around, deletes a gate and deletes a control, is basically a form of conditional fusion that we are doing right there. But that's not the case for all gate-level rewrites, because there are a bunch of gate-level rewrites that are really hard to express in the higher-level program language. The ones we found really tricky to do, and still haven't been able to figure out properly, is the merging of the CTU patterns together, or merging these multiple mismatch gates together, because it just results in patterns that you generally don't see in those higher-level languages, or they just don't support it easily. These CTU patterns and ancillas, while are visible in the program level, like with the with, do, undo block that we've been seeing multiple times in this presentation, that's not the case for all of these patterns. That's because some of these conditional statements, for example, can get lowered to its own CTU pair on lowering. And that's just not visible in the higher level program as easily. And there are a bunch of arithmetic operations, et cetera, that have the same features in Tower, for example. We find that the program level rewrites, if you apply them, can also hurt optimization on the gate level. And the reason the main example we saw was mainly with Spire, which is the compiler for Tower again, which comes with a bunch of like higher level, which comes with a couple of program level transformations. And in one or two cases, I think we saw that overall, applying all of those rewrites actually results in a worse circuit than when none of the rewrites were performed in the first place. And that can be just basically seen by depth, in the depth of the circuit after Spare is applied onto the circuit generated from the Spire compilation process for the same Tower program. There are more cases in the paper of the overall ablation studies that we were playing around with. Overall, we find that these compiler abstractions can create sources of inefficiencies in the circuit design or the final program you're going to be working with. Our compiler uses or targets these CTU patterns and ancillas in particular to bridge the gap between higher level program abstractions and gate level rewriting tools that have already existed for a while now. And overall, from this work, my main takeaway was that understanding the consequences of these abstraction choices that we are making is really useful. And as we have discussed in the paper, there's probably a lot more optimization opportunities that can be found by understanding what those abstractions lead to and how can we exploit them to find more optimization opportunities, and what's the trade-off for applying these rewriting optimizations between the higher level program in the middle somewhere, or on the gate level as we are working with, or even further down on the decomposed gate level of the final circuit. Thank you.
Thank you, Ritvik. People can step up to the mic with any questions.
Hi, Sébastien Bardin from CEA. I was wondering, in your comparison, I didn't see, did you check against optimization from Qiskit, typically?
Good. That's a good question. So one thing we had to like contend with was, depending on these circuits that we were dealing with, some of these can be compiled to simply Clifford to plus T pretty easily. And if you just throw Qiskit at it, and if you apply even like the smallest level of optimization, it will convert everything to U3 gates. And suddenly you're not dealing with the same gate set in the first place. So that was one of the main issues when dealing with Qiskit itself, where it just like converts. It is really good in like taking any Toffoli implementation and just finding, oh, these are places I can plug U3s in and make it much more smaller. But that's a problem that we like sort of don't want to like sort of tangle with, mainly because we believe that spare can be applied at a higher level anyway, above Qiskit, for example, where you can then, if you actually did want to use U3 gates and so on, you can just apply the Qiskit backend stuff once those once the circuits have been optimized. And just a quick note, the lowering optimizations that we're dealing with are very specific to this uncomputation pattern, and it's not something that, unless you're aware that this is a compute-uncompute gate, you can't really do that even at the lower gate level. And that was another thing that was basically missing from Qiskit.
Okay, thank you.
So I have a question.
Yeah.
So this spare IR, it sounds like it's pretty low level. Is it just like a circuit language with multiply controlled X's, or is there more going on there?
Okay. So that's a good question as well. So our IR that we wanted to work with, it is fairly low level. The way it works is you just have not necessarily multi-controlled Toffoli gates, but any kind of multi-controlled gates. And I'm trying to skip to the slide and I ended up going the wrong direction. Here. So all of our circuits are expressed as these multi-controlled single target gates in our lowering. And that was just mainly because it was much easier for us to reason about, oh, these gates commute, or these gates change one of the controls in this pattern, and so on. I mean, it would be useful to explore higher level IRs as well to see how that would work. And but yeah, finally, I think if you have any multi-control gate, what we ideally want is as high level representation of that multi-control gate, because often compiler tools would even decompose that down to some multi-control gates that use some ancilla, and then you need to lift that information.
And that's an issue for Feynman, the Feynman tool as well, I believe, because they have this MCX routine that they can do. So were you able to provide sort of intermediate circuits to Feynman to see whether it was able to optimize away the multiply controlled X's?
Yes. So the way we evaluated this was basically then for these circuits, we generate this. Once we are generating these circuits from such compilers, we make sure that they're as high level multi-control gates as we can get from these compilers, and then use the same circuit for spare as well as spare as well as Feynman. And we basically use the multi-control Toffoli decomposition, and we found that does obviously give you a large performance improvements, and that's why Feynman was one of the much better performing tools that we found when we were comparing all other benchmarks against spare.
I see. All right, very cool. Thank you. Our next talk will be a remote talk by Junyu Zhou. So I assume we're getting this up on the screen and active, but I don't know how much of a process this is. Junyu will be talking about Marksim, which is this tool for reconciling determinism and randomness in optimization and simulation.
Can you hear my voice?
Right, Junyu.
Okay, thanks. Thanks for the introduction. I'm Junyu, And currently, I'm a first-year PhD student from the University of Pennsylvania. And this summer, I'm working at Lawrence Berkeley Lab. So today, I'm going to present our recent work, Marksim. So this is a compiler optimization framework that integrates the strengths of both deterministic and randomized compilers for quantum Hamiltonian simulation. And this is a collaborative project with AWS Quantum Technologies. So first, let me give some background about the quantum Hamiltonian simulation. Here, we have a target Hamiltonian. It can be decomposed into several localized Hamiltonian terms, which is represented by the capital Hj here, with coefficient small hj. The evolution of this target Hamiltonian is given by a unitary matrix U, which is equal to e to the power of minus iht. A compiler can map this evolution onto a quantum chips. In practice, these capital Hj are usually polystrings, which can be represented by a tensor product of poly operators, here shown as sigma 1 to sigma n. And for each polystring, we can have a unitary evolution, which is unitary j equals to e to the power of minus I hjt. This is the basic building blocks for quantum Hamiltonian simulation, and there exists standard compilation process that can map this unitary onto the quantum circuit that we just like we show on this graph. And now we are going to show the two state-of-the-art compilers for Hamiltonian simulation. The first category is deterministic compiler. The strategy of this kind is trotterization. So instead of implementing the whole Hamiltonian at once, we implement each Hamiltonian term with a much smaller time segment, delta t. And then we concatenate them together to approximate original evolution. Usually the order of Hamiltonian terms is flexible, but will be fixed for a certain instance. We can define a trotterization steps equal to the total evolution time over the evolution time segment, delta t. Here is a circuit example. We can implement the first Hamiltonian evolution in the red box and the second Hamiltonian evolution in the blue box. And in the middle, in the yellow box, there is some opportunities to have gate cancellations. And a lot of research papers have studied this problem. The second category is a randomized compiler, with QDrift being a representative example. In this approach, we will still deal with these short time evolution terms. But unlike a fixed order implementation, the terms are now sampled from a distribution. This distribution is determined by the magnitude of each term's coefficient in the overall Hamiltonian. Terms with large coefficients are more likely to be sampled and executed. One key advantage of this randomized strategy is that it achieves a symptotically lower circuit depth compared with the deterministic Hamiltonian simulation method using trotterization. To summarize, we have two types of Hamiltonian simulation compilers. The deterministic compiler, which is optimized for gate cancellation, and the randomized compiler, which offers asymptotically lower circuit depth. The goal of this project is to combine the strengths of both approaches to achieve a more efficient quantum circuit implementation for the Hamiltonian simulation problem. Before talking about our techniques, we begin by introducing some key concepts used throughout this paper. The first one is Markov chain process. We consider a sequence of random variables, xt, where t typically denotes time. And these variables represent the state of the system at different time steps and take values in a state space S. A process is defined as a Markov chain if the probability of transitioning to the next state depends solely on the current state, rather than the full sequence of past states. This is known as the Markov property. If these transition probabilities remain the same across all the time steps, the process is called time homogeneous, meaning the transition rules are time invariant. To capture the probability compactly, we use a transition matrix P, where each entry Pij represents a probability of transitioning from state Si to state Sj. This matrix encapsulates the full dynamics of the Markov chain. And the next thing we are going to introduce is the example of the Markov chain process. So here we have a graphical representation of the Markov process. In this graph, each node corresponds to a state in the state space. And here we have 4 distinct states. The edges between nodes represent possible transitions between states, with the associated numbers indicating the transition probabilities. From this graph, we can construct the corresponding transition matrix P. Alongside the transition matrix, we will introduce another concept, stationary distribution, a probability vector pi that represents the eigenstate of the transition matrix P. In other words, it satisfies pi times P equals to pi. For this example, the stationary distribution can be easily calculated by solving an eigenvalue equation. Now we are going to introduce the concept of minimum cost flow problem, which also called MCFP in this project. This problem is defined by a flow network represented by a tuple V, E, C, S, T, where V is the set of vertices, E is the set of edges, C denotes the capacity on each edge, and S is the source, T is the sink. In this example shown, we highlight a flow from node 1 to node 2, denoted as F12. This flow must respect the capacity constraints, meaning that the absolute value of F12 is less or equal to C12. Additionally, each edge is associated with a weight, in this case W12, which represents the cost per unit of flow along that edge. So the objective of the MCFP is to determine a valid flow that minimizes the total cost, computed as the weighted sum of all flows across the network. Okay, with these two concepts in mind, we can introduce our techniques. First, I'm going to introduce an intermediate representation we developed for the Hamiltonian simulation problem, called the Hamiltonian term transition graph, or HTT graph. The HTT graph is a directed graph where each node represents a Hamiltonian term, and the edges capture the transition probabilities between terms. To interpret this problem, consider we approximate a quantum evolution by sampling individual Hamiltonian terms. And then we concatenate these sampled Hamiltonian terms and together to approximate the total evolution. For instance, at step k, we might sample a Hamiltonian terms e to the minus IH1. To determine the Hamiltonian term for next step k plus 1, we refer to the transition probabilities shown on the outgoing edge from the current node. So from node H1, we might have a probability P11 to stay on H1, P12 to transition to H2, P13 to transition to H3, and so on. These probabilities guide the sampling process and ultimately define the structure of the simulated circuits. It's important to note that the transition probabilities in the HTT graph are not arbitrary. They are subject to specific constraints. This is because in the final circuit, we want the evolution terms to appear according to a target distribution shown in this equation. This is defined by the relative strength of the Hamiltonian terms in the overall Hamiltonian. Mathematically, this means a desired distribution must be a stationary distribution of the transition matrix in the HTT graph. By ensuring this property, we can guarantee that regardless of any start point x, we will eventually converge to the stationary distribution. With this structure in place, we can now describe Q-drift as a special case of our HTT graph intermediate representation. In Q-drift, the transition matrix P is particularly simple. Every row is identical and matches the target distribution. This implies that no matter which Hamiltonian term is sampled in the current step, the next step is always sampled independently from the same stationary distribution. Using the HTT graph intermediate representation, we can show that our approach achieves the same asymptotic circuit depth as Q-drift, preserving the core advantage of the randomized compiler. The next question is, how can we incorporate the gate cancellation techniques as a key benefits of the deterministic compilers into the structure of the transition matrix? Addressing these would allow us to combine the strengths of both approaches in a unified framework. So this challenge can be addressed by solving a minimal cost flow problem to derive a transition matrix for the HTT graph that incorporates gate cancellation. In the first step, we consider a valid transition matrix using a flow model without considering any cost of quantum gates. On the left is a HTT graph representation. First, we split the nodes representing the Hamiltonian terms into two columns. The first column, labeled H-prev, represents the previously sampled Hamiltonian terms. And the second column, H-next, represents the terms to be sampled in the next step. We introduce a source connected to the H-prev to each H-prev, and assigning a flow value equal to the target distribution pi. Similarly, we add a sink connect from each H-next node, also with the flow values matching the desired distribution pi. And then we will connect each H-prev node to each H-next node, with edges carrying some flow. For example, the flow from H1 to Hn is denoted as F1m. By dividing this flow by pi1, which is the target probability of sampling H1, we obtain the transition probabilities pi1m. And other entries in the transition matrix P can be derived similarly using this equation. Transition probabilities defined this way form a valid transition matrix, and this can be formally proven. With the flow model in place, we now incorporate gate cancellation information into the edges between H-prev and H-next. Here we only consider the CNOT cancellation, while the objective can be changed to other gates. So this is done in a straightforward way. We assign each edge a weight equal to the CNOT gate number required for transitioning from the current term to the next. Using these weights, we then solve a minimal cost flow problem. This approach helps avoid transitions with high CNOT cost during the sampling process, while still ensuring valid convergence to the desired stationary distribution, or the original unitary evolution. And the next issue is that although all the transition metrics we construct will eventually converge to the target distribution, their convergence rates can differ. To accelerate the convergence, we introduce a method called random perturbation and matrix combination. In this approach, we first apply a small random perturbations to the weight in the flow model, generating multiple valid transition matrices. We then combine these matrices using a convex combination. The combined matrix typically achieves faster convergence as confirmed by spectral analysis. As illustrated in this figure, in the figure below, the spectrum of the combined matrix shown by the orange line is tighter than that of the original matrix without perturbation, which is shown in the green line. Theoretically, a tighter spectrum implies a faster convergence to the stationary distribution. Okay, now I will introduce the evaluation part of the Marksim. First, let's look at the experimental setup. We use 3 transition matrices to guide the sampling process of the Hamiltonian terms. The first transition matrix is PQD, is the baseline matrix from QDrift. The second one, PGC, is the matrix incorporates the structured gate cancellation techniques. And the third one, PRP, is generated using random perturbation techniques. We evaluate 3 configurations. The baseline only uses PQD. The configuration Marksim GC combines PQD and PGC. And configuration Marksim GCRP combines PQD, PGC, and PRP. For benchmarking, we select a variety of ions and molecules with qubits counts ranging from 8 to 14. Let's start looking at the overall improvements. In the graph shown, the blue curve represents the CNOT count for the baseline configuration across different accuracy levels. The green curve corresponds to Marksim GC, and the yellow curve corresponds to Marksim GCRP. On average, we observe a 25% reduction in CNOT count for Marksim GC and a 27% reduction for Marksim GCRP. This demonstrates the effectiveness of incorporating gate cancellations through the MCFP formulation. Additionally, as suggested by our theoretical analysis, introducing randomness improves the convergence in the sampling process. As a result, Marksim GCRP achieves a 8.3% reduction in standard deviation compared with the Marksim GC. The next experiment examines how different combination ratio impacts CNOT gate cancellation. We present 4 curves in the graph. The blue curve represents Q drift with no gate cancellation, and the green curve corresponds to a small proportion of gate cancellation. And the yellow curve reflects a moderate ratio, and red curve represents the highest ratio of the gate cancellation matrix. As shown in the table, the red curve lies at the, as shown in the graph, the red curve lies at the bottom, indicating the greatest CNOT cancellation. The result clearly demonstrates that increasing the ratio of the gate cancellation matrix leads to a greater CNOT gate reduction. Finally, we evaluate the impact of varying the evolution times for the ions and molecules. And our result shows that across different evolution durations, we achieve an average CNOT reduction of around more than 20%. And this is all the result. Thanks for your listening. And if you have any questions, please feel free to ask.
All right, thanks, Jianyu. We have time for a few quick questions.
Hi, thanks for the great talk. I had a couple of questions. One was, I think, do you guys believe that you can use this kind of a framework for accelerating how a simulation of the Hamiltonian simulation on a classical computer, if you're using, if you're simulating the quantum computer on the classical computer with a tensor network or something? Do you think like this could be applicable there? And the second question was just like, yeah, sorry, first please.
Yeah, please continue the
Please
second
go ahead.
question. Yeah. So I will answer the first question. This framework can be only applied to a quantum regime because we are object some metric like the CNOT numbers. But if you are considering apply this framework to a classical simulation, I think you can, for example, you can calculate the GPU times, maybe the GPU times you need to simulate between different Hamiltonian terms and try to apply this as the weight of the MCST. I think the minimum cost flow problems. And I think by applying this metric, you can using this framework to accelerate your classical simulation. I think it's possible.
That makes sense. That makes sense. Thank you. I think the other quick question was just, how do you guys think of like this being applied on like quantum computers which are basically doing time evolution directly, which do not have a circuit abstraction and so on? So like,
could you rephrase your question again?
So I was just asking, like, how do you think this would work with a D-wave-like system? Is basically my question. Where you just
you mean D-wave?
Yeah. That kind of a hardware.
I mean, this only applies to digital quantum computers. I mean, for D-wave, they are analog quantum computing paradigm. It's different from this one. I'm not pretty sure how to apply this to their device.
All right, that makes sense. Thank you.
All right, let's thank our speaker again.
Okay, thank you so much. Bye.
All right, our next speaker will be Zhicheng Zhang, who will be talking about a quantum register machine, and we'll just give him a minute to finish getting set up. And cool. Hopefully the screen is about to pop up. Oh, right. Take it away, Shichang.
Cool. Thanks, Robert, for the introduction. I'm Zhicheng, and I'm going to talk about our work on quantum register machine, efficient implementation of quantum recursive programs. And this work was done in collaboration with my supervisor, Mingsheng Ying. Let's start with the question why we consider quantum programming. So this is just like the classical PL. It serves as a bridge between the human and the machine. And for the programmer, we have high-level quantum programming languages that provides you a convenient description of the quantum algorithms. And for the machine side, we can compile these high-level quantum programs into low-level quantum circuits, maybe through multiple steps. And the quantum circuit will be finally executed on the quantum hardware. So there are two goals we hope to achieve in this whole process. First, we want the high level to provide a convenient description for the programmer. And also, we hope this compilation process can yield an efficient implementation of the programs. Okay, great. So why we consider quantum recursion? Maybe we should ask why we consider the classical recursion. And in the imperative programming languages, this is often supported by the recursive procedure calls. And one typical example of using recursive procedure call is the divide and conquer method. So you have a large problem, you divide it into several subproblems, and you call procedures to conquer each of these subproblems. And of course, the procedure you're calling can be the same as the procedure you are defining, but maybe with a different parameters specifying the size. So this allows you to encode very complicated computation in an elegant and compact way. And there are a lot of examples of that. Okay, so what's new in quantum programming? In programming, we have data and control flow. Of course, in quantum computing, the data can be classical or quantum, and here we just focus on the quantum data. And for the control flow side, we have two types of control flows in quantum programs. One is the classical control flow, and one is the quantum control flow. And the quantum control flow is just the superposition of program execution. So it is often guarded by the so-called quantum if statement, which compared to the classical if and else statement that conditioned on the Boolean expression. But here we are conditioned on a qubit variable, which can have this state being in superposition state. For example, you can write it as alpha kit 0 plus beta kit 1, where alpha and beta are complex number. And condition on the state of Q, you go to the first branch and the second branch, and they are quantum branch. And you execute both the branches together in superposition instead of going just one of the branch. And you can alternatively write out the unitary describing this qubit statement as a combination of controlled unitary for each of these branches. Okay, great. So once we have these two programming features, the quantum control flow and the recursive procedure call, we can arbitrarily combine them, and this naturally induces the quantum recursion. And there are also many examples of quantum algorithms that can be written as elegant and compact quantum recursive programs. And here I should mention that the recursion we are considered here is the most general form of quantum recursion. So you can arbitrarily interleaving these two programming primitives. That means when you are defining some procedure, you might define some quantum if statement inside, and it creates a quantum branch. And each of the branch you can call other procedures. And in the definition of that procedure, you can also have internal quantum control flow. And you can again call other procedures, and the procedure can be done in a recursive.
Like the linear combination of unitaries, Hamiltonian simulation, quantum state preparation, HHL algorithm for the solving quantum linear systems. And it is just a combination of this controlled UX. And there is a straightforward way to implement this unitary by taking the sequential product of this control UX. And obviously, this time complexity for implementing this straightforward way would be proportional to the summation of each TX, the time complexity for implementing each control UX. there is also a parallel implementation for this quantum multiplexer, which can achieve a better parallel time complexity proportional to the maximum of Tx, which is exponential better than the straightforward way, but it comes at a price of manual design of complicated quantum circuit. So a natural question is, can we design at high level and still obtain such kind of efficiency? And this question, of course, goes beyond these specific examples because we are considering programming languages. Okay, so using the quantum recursive program, we can do it. We can describe the quantum multiplexer as a quantum recursive program in the language RQC++, which is defined in our previous work. So here you can see the key procedure is this PKX. And in the procedure body that defines this procedure, we have this quantum if statement, which creates two quantum branches. And in each of these branches, we will call the procedure PKX itself, but with different actual parameters. Okay, you can see the interplay between these two features, and intuitively, this allows you to check these controlling qubits in a recursive way. So you are recursively collecting this control information, create exponentially many quantum branches, and then at the bottom layer, you just call each of the procedure QX for implementing the UX. Okay, what's good about these programs? First, it is elegant. Second, if you further have a way to compile this program and implement in some machine that supports this recursive procedural call and quantum control flow, then you can execute these two quantum branches in superposition together. So that means for these exponentially many quantum branches, the running time, the overall running time of this program will only depend on the longest quantum branch. That will induce a maximum of Tx. Okay, so now for our contribution in this work, we propose a comprehensive implementation process for quantum recursive program, and this is based on a new architecture called quantum register machine. It is an abstract architecture accompanied by an instruction set QINS and provides instruction level support for quantum control flow and recursive procedure call. And the implementation process go from you first compile high-level programs in RQC++ into instructions in QINS. Then at the instruction level, you can execute this compiled program by loading it into a quantum random access memory. But to handle the quantum control flow, we also need to do the partial evaluation. I will introduce it later. And then we can execute on the quantum register machine, and finally, this will be converted to quantum circuit. And if you analyze the final complexity for this implementation, it gives you some bonus of automatic parallelization. For example, for the quantum multiplexer program, it automatically yields a parallel implementations. Great. So for the architecture, here is quantum register machine, which works like classical CPU. So it will first store the compiled program into a so-called quantum random access memory, which is a quantum counterpart of the classical RAM. And it will fetch instructions in each instruction cycle, then decode and execute the corresponding instruction and move to the next instructions, just like the classical CPU. And we also have all these storage components becoming quantum. We have quantum registers, which consist of system user registers, and we have this quantum random access memory separated in several sections, one for the storing the program and for storing the quantum data and the stack. Okay, so here, how to handle the quantum control flow. Inspired by the previous work called Quantum Control Machine, which borrows some ideas from the classical reversible architectures, we put a program counter into a quantum register PC. So PC just points to the current instruction you are executing. And of course, it is a quantum register, so it can be in superposition state. It can point to many locations in this program section. So you can execute these programs in superposition. Okay. So what is a new challenge when you consider quantum recursion, not just the quantum control flow? Now you have recursion, and recursion will introduce some non-determinism. So here is a problem called synchronization problem. That's roughly speaking, if you executing a QIF statement, you create two quantum branches, and they might have different termination times. So if you want a single CPU to execute both branches in superposition together, you have to synchronize these two quantum branches. And you might have nested quantum branches created by this recursive procedure call, and you don't know how many of them. So you need to automatically handle this problem without changing the program text. So our solution is by partially evaluating the quantum control flow, and this step is independent of the quantum data. It only needs the classical input, and we can collect this result into a data structure called QIF table, and it will also load it into the QRAN to aid the execution of the final compiled program. Great. And to handle recursive procedure call, this is just like the classical. You allocate the call stack in the QRAM. And one important thing is everything here is quantum, so they can be in a large superposition state. These registers and QRAM, they can be quantum entangled. Here is an instruction set QINs, which is a set of instructions specifying what the CPU should do when you fetch instruction and decode these instructions. So most of them are borrowed from the classical reversible architecture, but here we introduce the most important part is we introduce two instructions for handling the quantum control flow, and these two instructions allows you to inherit the high-level structure in the high-level quantum recursive program. So you always keep this structure, you can track the entanglement, and that allows you to handle this quantum control flow. And you can write out the decoding unitary for implementing these instructions, decompose it into elementary operations on register and QRAM. Maybe I should skip some part of this implementation process. So first step is compilation, which just consists of 3 passes. Let's look at an example. So here is for the quantum multiplexer program. On the left-hand side is after the first pass, high-level transformation. So you just introduce some new variables to simplify the structure. And on the right-hand side is after high to mid-level translation. Here we focus on the procedure PKX. It is a procedure declaration. And so at the beginning, just like the classical case, we first initialize these formal parameters. Then we handle these classical assignments. And since classical assignments are irreversible, we need to introduce garbage data. And these garbage data will be automatically uncomputed at the end of the procedure body. And we also have these quantum control flows. We have this QIF and FIQ, which marks the beginning and the end of the quantum control flow. And you have these procedure calls, which need to operate with a stack, because you need to handle recursion. OK. Now, the key point is this part, the partial evaluation. So remember, our target is to automatically handle the synchronization problem. So on the left-hand side, you have these unsynchronized quantum branches. And if you want a single CPU to execute all these branches in superposition, you need to promise that they terminate at the same point. That is the synchronization. And the difficulty is introduced by the recursion. You might have non-deterministic number of nested procedure calls. So how to handle this problem? Actually, you need to use the feature of the high-level programming languages, RQC++. Once you have the classical input, but you don't need to know the quantum input, you can already evaluate and calculate the number of steps for number of instruction cycles for each quantum branch to wait for the other quantum branch. So you can, when you set the practical time tpreg, within this time, you can partially evaluate the quantum control flow and collect all the information into a data structure called QIF table. So here is a QIF table, which is a data structure recording the history of all quantum branching. It is a graph, and in each node of this graph would be an instantiation of the QIF statement. For example, you go to this QIF statement, you create an instantiation of this node, then you might call do a recursive procedure call. You call the procedure again, and you enter this QIF statement again, and you will create another instantiation. So there are some nesting and non-nesting relation between these nodes. And when you do the partial evaluation, you only need to know the classical input, and you can determine how many number of steps I need to wait at each node to synchronize both quantum branches. Great. Finally, for the execution, we just load everything into the QRAN, including the compiled program and the partial evaluation result QIF table. And what the quantum register machine does is like the classical CPU. In each instruction cycle, you keep repeatedly doing this fixed unitary ucyc. And in each ucyc, you need to check the QIF table to determine whether we need to wait at the current instruction cycle. And if you don't need to wait, you do the execution. This is like the classical case. You do the fetch, then decode and execute, then unfetch and handle the branching instruction. And here the decoding unitary is where we just mentioned previously. It's a fixed unitary. Okay, and actually we can analyze the efficiency of the above implementation. It can use automatic parallelization for certain subroutine like the quantum multiplexer, and it automatically use exponential improvement over the straightforward one. Okay, the final take-home message is quantum recursive programming can be win-win. It provides you both the convenient description and the efficient implementation. So you can try it in the design of quantum algorithm protocols. Finally, there are several future topics. This is just a theoretical framework for the compilation. So the immediate next step is the software implementation. And of course, we can extend the features of the programs. And there are a lot of optimization opportunities in this whole process because you have multiple steps. And also, there is an interesting question is whether we can obtain more algorithmic speed up from the programming language perspective. And here is an additional resource of a mini course I gave on quantum recursive programming, and you can check the recording through the link. Thank you, and I am happy to take any questions.
Thank you, Zhicheng. Questions? Oh, good. I get to start.
Sure.
So can you talk a little bit about the restrictions and limitations? Because there's all these problems. If we have quantum recursion, we could have a branch that goes on forever, and there's no reasonable way for me to implement that. I could try to control on the same qubit that I am trying to use. There's all sorts of things that can go wrong, and I know Charles Yuan talks about this in his quantum control machine, and Badescu and Panganen have talked about this a lot in their prior work. So yeah, tell me about the restrictions and how you get around these problems.
Thank you for this great question. So the question is about the limitation and the restriction of these quantum recursive programs and quantum register machines. So let's go back to the programming language. First, for the RQC++, here is just an example, but actually I prepare a syntax for the RQC++. Okay, so this program can only describe unitary operators. So here temporary doesn't consider the measurement, and this will make it consistent with the observation previously made in the quantum control machine paper. It is easier to handle the unitary when you consider the quantum control flow. Okay, so this is one of these restrictions, and another maybe kind of limitation is what you mentioned. You might have infinite loop. So actually this is an unavoiding issue because in classically you also cannot determine whether the loop will terminate, right? So here actually we set a practical time t-prac. You just check whether this program might terminate within this practical time, and I think this issue is it is hard to avoid these issues. Okay, these are two restrictions of the program and implementations.
Cool.
Thanks for the nice talk. I was wondering, in classical programming, there is this close connection between loops and recursion, like you can rewrite them. Can you do something similar here also, or can you comment on this?
Great question. So the question is whether you can converting some of the recursion into the loop, like in the classical case, you have the tail recursion and you convert it into the loop. My personal opinion about this is might be hard in the quantum case because you are creating multiple quantum branches using the quantum control flow. And when you try to convert it into a quantum while loop, like what is introduced in the WQS workshop by you, yeah. You need to, so the quantum while loop, first, the definition might not be able, at least in this current form, to describe the exponentially many quantum branches, right? And in our case, when you do the recursion into two quantum branches, you might do different. You can call different procedures. So that means it will create more quantum branches. That makes it hard for describing into the quantum while loop. And of course, it might not be a tail recursion. It can be arbitrary recursion. Before the procedure call and after procedure call, you can have arbitrary things as long as follow this syntax.
Okay,
yeah.
Thank you.
All right, let's thank our speaker again.
Thank you.
Our next speaker is going to be Nathaniel Torno, and he's going to be talking about a quantum VM. So we'll give him a minute to set up, and then I'll take it away.
Okay, does it work, the mic? Okay, perfect. So hi everyone. Oh, sorry, have you? Okay. Hi everyone, I'm Nathaniel, and I'm happy to present you our work on QVM, Quantum Gate Virtualization Machine, which I did together with Manus Giotamis and Professor Batutia at TU Munich and Leibniz Supercomputing Center. So as you all know, quantum computing promises to solve lots of hard problems across a range of applications in areas like material science, quantum chemistry, cryptography, or maybe even machine learning. And to allow us to do these quantum computation, we have also seen rapid development of quantum processing units, or QPUs, with companies focusing on superconducting circuits, ion traps, or recently neutral atoms to realize such quantum processing units. When we talk about quantum programs, so programs that can actually run on these quantum QPUs, we've already seen, we talk about the quantum circuits, which can be represented as this assembly format that you can see on the left, or as a nice circuit diagram as you can see on the right. When we do a quantum computation, we always start by initializing some qubits, followed by doing some operation as gates, which are single qubit gates or multi-qubit gates that change the state of these qubits, followed by, in the end, a measurement to get some information about the state of the qubit after our computation. When we talk about quantum programs that are actually useful for solving real problems, we are interested in two main metrics of these quantum circuits, which are the width, so how many qubits we can execute our circuit on, as well as the depth, so how many operations we can do after each other on the quantum circuits. And real-world application, we need to run really deep and wide quantum circuits. So, of course, we haven't seen any significant breakthrough in quantum computing yet, so why are these metrics still limited? So width is, of course, limited by the number of physical qubits that we can put on our quantum chips, and depth is limited by the error per operation of our operations on the QPUs, as every operation introduces some noise to the computation, such that these errors propagate through the circuits and get larger and larger, such that we have an increasing chance of failure of our computation at the end of the circuit. So to put this finally into perspective, where we are right now, we are in this era of QPUs, where we have QPUs of hundreds of qubits and error rates of 1 or less than 1%. And you would need to go somewhere here to do some meaningful, or it is believed that we need to go somewhere here, which means that we have to do an orders of magnitude improvement in both the number of physical qubits and the error rates per operation. So how can we get there? One promising solution that has been around now for a while that could help us get there is a solution called gate virtualization, which allows us to virtualize 2 qubit gates as a combination of single qubit gates. So as you can see here in this example, we have a circuit on the left where we have a 2 qubit gate in the middle. And what we can do is we can write this as the same expression on the right, where instead of the 2 qubit gate, we run some circuit instantiations I, where we insert some single qubit gates instead, which in this case allows us to actually run these circuit instantiations as 2 independent subcircuits. And then in the end, we need to do some classical reconstructions to get the same result as if we had executed the circuit on the left. So gate virtualization has 2 opportunities that we can utilize theoretically for scaling depth and width, which are circuit cutting and dependency reduction. So circuit cutting is very helpful if we have some large quantum circuit and we want to run this on a small QPU, which in this case, of course, doesn't work since we have more qubits in our circuit than in our physical QPU. So what we can do is we can just virtualize this gate in the middle, allowing us to decompose the circuit into multiple smaller subcircuits, which now fit easily on the smaller QPU. Dependency reduction is very helpful if we want to minimize the error propagation in the circuit. So in this example, we have a small circuit here, and we can imagine that some error will happen here at the beginning of the first qubit. So what will happen is actually this error will propagate theoretically through the entire circuit due to the dependencies between those qubits and operations, leading to errors on every qubit at the end of the computation. However, if we now decide to virtualize this gate, what would happen is that an error occurring on the same qubit will now only propagate to 3 qubits, so that the third qubit here is actually independent of this error, which allows us to construct more circuit with more depth as we have less error propagation. So circuit cutting has the potential for us to gain more width in quantum circuits and dependency reduction for more depth. However, gate virtualization, of course, doesn't come without costs. So actually it has some overheads, which can be illustrated right here. So if we want to virtualize some k gates in our circuit, what we need to pay is quantum processing cost of 6 to the power of k subcircuits that we need to run. And we need then to also post-process these results classically using 6 to the power of k floating point operations. And these values come from theory, so you have to believe me on that. So unfortunately, we have some high exponential quantum classical overheads that we need to get around. So to recap, we've seen that gate virtualization has strong potential in scaling depth and width of circuits, but it also has these super high exponential overheads, unfortunately. So in this work, we ask ourselves, how can we still leverage gate virtualization to do some gate virtualization before the overhead gets too large, to still leverage this to scale our depth and width. So to this end, we proposed QVM, which is a system to use gate virtualization for scalable and reliable executions for circuits on this QPUs. And we made 3 core contributions, which are: first, we allow for a programmable and efficient gate virtualization by coming up with a small IR to do efficient analysis on the circuits and apply virtualizations. Secondly, we try to apply optimal gate virtualization by coming up with a compiler, a small compiler that applies those virtualizations to circuits. And finally, we try to virtualize as many gates as possible with our QVM runtime, which allows for a parallel execution of both quantum sites and classical post-processing. So now, after motivating the problem, let's look at how the system looks like. So this is kind of where we are, where we want to execute some large quantum circuit, but we only have some small QPUs and some classical nodes at our disposal. So for running this circuit, QVM comprises of 2 main components, the QVM compiler and the QVM runtime. So if we now pass the circuit to execute, what would happen is we pass it first to the front end, which emits some virtual circuit IR, which gets passed to the optimizer, which has 3 main optimization passes: the circuit cutter, dependency reducer, and qubit reuser. After optimizing this IR, we pass it to the code generator, which generates some QPU-optimized virtual circuits. To run the virtual circuit now, we pass to the QVM runtime, which comprises of the virtualizer, which is the main brain of virtualizing quantum 2-qubit gates. And it has the instantiator, which is for instantiating these different subcircuits, as well as the knitter, who does the parallel processing on many classical nodes, as well as the instantiator uses a scheduler to schedule quantum circuits on many small QPUs in parallel. So yeah, the talk I will focus on these 2 main optimization passes, starting with the circuit cutter. So the circuit cutter, we need to solve an optimization problem, having the constraint that we want to cut the circuit into multiple subcircuits with a size S, which could be a QPU size. And we have a budget B of a maximum amount of gate virtualizations that we can do, so to constrain kind of the overhead. So our goal is to cut the circuit into subcircuits with smaller than S qubits with not more than B virtual gates. So to this, we use a qubit graph, which is in our virtual circuit IR, which models kind of this qubit connections, where the vertices are qubits, and we have an edge between 2 vertices if there is a 2-qubit operations between those 2 qubits. So for example, if we have here between the qubits 3 and 4, we have 2 2-qubit operations. leading to us having an edge between those two vertices with a weight of 2, since we have two 2-qubit gates. So to do these optimizations, so here we want to cut to 3 qubits, subcircuits, and we have a budget of B equals 2 virtual gates. So what we will do is we take this graph and we will do some partitioning of the circuit using our favorite gate partitioning algorithm to minimize the weight of cut edges and to kind of fulfill these constraints. So this would lead us to virtualize these two qubit gates right here, giving us the virtual circuit on the right, which fulfills the constraints that we had in the beginning. So let's talk about the dependency reducer. So for the dependency reducer, we also need to find the solution to an optimization problem where we have the constraints that we have some budget B, and we want to minimize the operation dependencies. So here we use the operation graph of our virtual circuit IR, which models the dependencies of the gates, where we have vertices being 2-qubit gates, and an edge between two vertices if there is a direct dependency. So here there's a direct dependency between gate 1 and gate 5, such that we have an edge between those two vertices. And what we do here is we take our dependency graph and we try to find the optimal nodes to remove from this graph to minimize the dependencies, which we can do, of course, optimally, or a good heuristic is also to just remove central nodes in the graph. So this would lead us then to visualize this gate in the middle, giving us this dependency graph, and giving us this new virtual circuit, which reduces the operation dependencies in this circuit. So finally, let's talk a bit about the results of our paper. So we have implemented a prototype of this system in Qiskit, and we try to focus on two main research questions of the impact of the circuit cutter and dependency reducer, but we have many more results in the paper. And we compared to Qiskit, and we actually did the experiments on real quantum hardware with the IBM Perth and Kolkata devices, and benchmarked on many NISQ applications. So here for the circuit cutter, we tried to compile to 7 qubit subcircuits, and we measured the fidelity of, so how good the result is of running the circuits, where higher is better, and we did this for 10 and 14 qubits. And yeah, we had 2 main setups, so the small QPU with QVM and the large QPU with QVM and the baseline. And note that we cannot even run the baseline on the small QPU since we have more qubits, so 10 and 14 qubits, so more than actually would fit on the small QPU. So we can see that on the same machine, we vastly outperform the baseline with our approach, and sometimes even on the smaller and worse machine, we also outperform the baseline, while being sometimes the same or worse. So we can effectively double the circuit width while maintaining or sometimes even improving fidelity. And yeah, the dependency reducer we compiled, I think in the interest of time, I can just say that we also minimize the qubit dependencies and relative circuit depth using our dependency reducer by 50% almost, such that we have a 1.7 times dependency reduction, leading to a 1.6 circuit depth reduction. So to conclude, we've seen that gate utilization is promising to scale depth and width of quantum circuits. However, it's quite complex and limited due to its overhead. So we proposed QVM, which is the system to leverage this gate utilization for noisy intermediate scale quantum computers. And we were able to effectively double the depth and width of quantum circuits to run on these QPUs. So feel free to check out the code. It's on GitHub, and also our ongoing research to further reduce this virtualization overhead with tensor networks. Thank you.
All right, thank you. Questions?
I think you might have preempted the question with the last line as well. So are you guys looking at basically calculating entanglement in different places to reduce the figure out a better way of doing dependency analysis or something like that? Or are you trying other things as well with it, is I think my question.
I mean, the technique itself is independent of entanglement, but I think it's kind of looking at how kind of interconnected some subparts of the circuit are, which, I mean, it's kind of the same as entanglement. if you have normal circuits. But yeah, that's what we're doing.
Yeah, that makes sense. Yeah, that's why I was like, oh, are you using tensor networks for dependency analysis or something else as well? Thank you.
Could you talk a little bit about the benchmarks you were running against? Because it's, as I understand this, highly entangled connected circuits would be very hard to virtualize because you would have to virtualize a lot of gates to split them across. So can you talk about both the benchmarks that you used and the limitations of the technique?
So yeah, as I said, these benchmarks were used, NISC benchmarks, which are not as highly entangled as they're for those noisy QPUs. So their virtualization works quite well, but of course, if you have like a QFT interconnected all the way, then this would not work for scaling it too much. So it works quite well if you have, for circuit cutting, to have circuits that have some very highly interconnected part, and between them they're not as interconnected. So for this, it works perfectly. Also for this application where you have just linear entanglement sometimes or something like that. So there it works, but it doesn't solve fault tolerant algorithms.
But when you say NISC, you're not thinking of like these random circuit experiments, because I think those also leverage a lot of entanglement.
Yeah, probably like, yeah, if you have too much going on, then yeah, it wouldn't work.
Okay.
Thanks for this nice talk. I was wondering if it is possible to combine your techniques with quantum multi-programming. So here you are considering when you are executing a large quantum circuit, you cut it into smaller ones that can be executable. So there are also cases where you want to execute many small quantum circuits on a large quantum computer. Do you think it is possible to combine these two techniques to handle different cases?
Yes, definitely. So I haven't looked at this in this work, but in case you can implement your scheduler to also schedule through this sub-circuit onto the same QPU. And we have also looked at this at another work in a quantum operating system that we did, which is at OSDI this year. So
very cool.
This,
All right, let's thank our speaker again.
Thank you.
Okay, and for our last talk, Qifan Huang will be talking about verifying error-correcting programs, which is exciting. So I'll give him a moment to set up.
Okay, put in pocket.
All right. Take it away.
All right. And so there's something wrong with the adapter? Okay.
Just give it a sec.
Okay. So okay. Thanks for the introduction. And good morning, folks. I'm Qifan Huang from the Institute of Software, a Chinese Academy of Sciences. And it's my honor to introduce the efficient formal verification framework for QEC programs to you. Okay. So we are undergoing an era where quantum computers are flourishing. So specifically, we utilize qubits as the fundamental computing units, which can be in superposition states and to achieve the speed up and reduce the base overhead. And there are currently several technical roadmaps to realize those physical qubits, such as superconducting, trapped ions, and the neutral atoms. And they have made advances in both the qubit lifespans and scalabilities. However, operations over physical qubits are itself noisy and unreliable, which makes it impossible to directly implement quantum algorithms on those quantum computers. Okay, so that's why we need quantum error correction. So to be accurate, we encode many noisy physical qubits into a code space to form logical qubits, which yields a much lower error rate. And there have been experiments over several hardware platforms to demonstrate the power of the quantum error correction. For example, Google's surface code experiment. The figure here shows the construction of code in this experiment and its ability to exponentially suppress logical error rates with the increase of the code distances. So here comes the question. And the critical challenge for QEC is that qubits suffer from not only bit flip errors, but also phase flip errors. So here comes the question. How to design a QEC code that corrects all of the errors? And to this end, we introduce the notion of stabilizer code. Assume that the errors are all poly-based errors, and the single qubit error channel is the depolarization channel. So, and the poly strings are tensor products of polys with phases, and the poly groups contains all of the n-qubit poly strings. Okay, so the stabilizer is thus a subgroup S from the poly group Gn with a constraint -I not in S. And the code words are all of the vectors in the subspace stabilized by S. So it means the common +1 eigenspace of the elements in S. So, and we thus can protect the qubits by ensuring that the encoded state stay in the code space. And for example, the code space corresponding to the stabilizer generators Z1, Z2, and Z2, Z3 is the span of 000 and 111 state. Okay, so let's take a look at a simple example, the 713 Stini code, which encodes 7 physical qubits into a logical qubit by projecting the initial state 0 and 1 into the code space using the following stabilizer generators. And the distance is 3, so it can detect and correct all of the single qubit poly errors. And besides, the Stini code itself is a self-dual CSS code by construction. So it is convenient to implement fault-tolerant logical Clifford gates over it, which we call transversal logical Clifford gates. And now we are going to consider the description of error correction procedures and logical operations. So one high-level way to describe this is via imperative quantum programs. And here we adopt a classical quantum programming language and implement the error correction procedures and the logical operations. And this table illustrates the programming implementations of the transversal logical Clifford gates and a error correction block building upon the Stini code. And we decompose the QEC block into 5 steps. The first, the logical operation, then the error injection procedure, followed by the syndrome measurements and the external decoder code, and finally the recovery operations. Okay, so the critical problem is how to verify that a QEC program, a QEC protocol has been correctly implemented following this program implementation. And there are indeed several approaches, like performing numerical simulations with tools such as STIM, or using other verification techniques such as symbolic execution and program logic. In this work, we apply the Hoare-style program logic to be explicit. We use the Hoare triple PSQ. We construct the specifications P and Q using about the program state in a mathematical way and the reason about the precondition and postconditions. And there are indeed works that pave the way for using the program logic to reason about QEC programs. And the critical idea is to emphasize the function of stabilizers in both assertions and the programs. However, besides this important inspiration, there are still challenges that prevent the birth of an efficient verification framework for QEC programs. So, the challenges we face can be broadly categorized into 2 aspects. First, there still lacks of the program logic that supports the backward reasoning, without which the completeness of the classical assignment cannot be ensured. And on the other hand, how to deal with the hybrid classical quantum verification condition still remains the open problem. So, to efficiently tackle these challenges, we propose a verification framework for QEC programs. We first designed a novel assertion language which possesses concrete syntax and established a sound proof system for QEC programs. And second, we show how to handle the verification condition efficiently. And finally, we implement a practical tool consisting of 2 modules. We first formalized the program logic and the proof system in Coq, prove the soundness of the proof system, and then implement a automated verifier for QC programs with the aid of the SMT solvers. Okay, that's all for the background, and let's get down to the business. So I'll first show you how to design the program, the assertion logic. So first, we extended the integer array with the square root of 2, and extended the concept of polystrings into to form the poly expressions shown here, PXP. Okay, so notice that the T gate will transform the polystring into the sum of 2 polystrings, and thus we introduced the additive predicate P1 plus P2 to represent such expressions. Okay, the definition indicates that the PEXP is indeed closed under Clifford plus T operations. And next, we adopt Boolean and the poly expressions at the atomic propositions and use logical connectives to construct the assertion language. We further interpret those assertions as subspaces of a Hilbert space and do a pointwise lifting from quantum logic for other logic connectives such as and or implications. And you can see that the semantics of poly expression P precisely align with those of stabilizer codes, just a modest extension to include additive predicates. And below is an example shows the expressive power of using quantum logic as a base logic. This is a simple measure in a recovery program. So it says that any initial state, any state initialized in the eigenstate of +1 in the first qubit will be projected into the eigenspace of Z2 upon measurement, and then return to +1 eigenspace of Z2 upon recovery. Okay, therefore the whole triple here is correct. However, derivation and the measure and case rule tells us that the weakest precondition will be A0 and A1. Okay, if we interpret the OR symbol here as the classical disjunction, then the weakest precondition, the semantics of weakest precondition is just the set of the eigenvectors +0 or +1, but not the span of them, so which induces an error. Okay, then let's move on to the program logic. Our programming language is a subset of classical quantum programming languages, in which we put the restrictions over unitary operations, but still being able to express all possible quantum operations. And we designed a proof system where we perform direct substitutions of the terms in the predicates. And among the rules in proof system, we specifically design some of them, making it sound and convenient to implement. For example, for the qubit reset operations, we find that it is equivalent to first measure the Z operators and then perform X recovery if the syndrome got flipped. And for 2 qubit unitaries, we construct a substitution over elementary poly expressions as shown below. And we have proved the soundness of this proof system through both manual derivations and formalizations in Coq. Okay, to further reason about QEC programs, we need to model possible occurring errors in the program. So therefore, we introduce a syntax sugar to replace the condition rule. If B, then U operates on QI else skip. The advantage of using this syntax sugar is that we can greatly simplify the if rule in case of poly operators. The inference rule for this syntax sugar is presented as follows. And besides, we also include the for loop as a syntax sugar for program sequences. The example shows that how to use the inference rule to derive the precondition starting from postcondition. We could see that the conditional poly operators just will only change the faces of the stabilizer generators, thus giving us an inspiration to simplify the verification conditions, as I will introduce in the next part. So next part is about how to deal with the verification condition. So first, you need to notice that when verifying a correctness formula shaped like PSQ, you have to first using the inference rules to derive the weakest precondition P prime, and try to prove that P entails P prime. That is called the logical formula P entails P prime is the verification condition will have to be dealt with. Yeah, and generally speaking, the verification condition P entails P prime is hybrid classical and quantum, making it difficult to determine whether it is correct. So it is hard to check whether such a verification condition suffices. But for QC programs, we can push things a little bit forward by noticing that for QC programs, the verification condition have a common form shaped like this. So let's give a little bit insight into this verification condition. Okay, in the left-hand side, PC is a classical assertion modeling the properties of errors. And errors may change both the form of the Pauli expressions and their phases. So therefore yielding the alternated stabilizer generators GI prime and the logical operators the LJ prime. So to simplify the verification condition and determine whether it is correct, we have to analyze the commuting properties of the stabilizer generators and the logical operators GI and LJ and GI prime and LJ prime. So let's do a case analysis. So first, we deal with the case where all of the Pauli expressions commute with each other. In this case, the classical quantum verification condition could be directly reduced to a classical assertion which can be solved by an SMT solver. If all the operators in the right-hand side is included in the left-hand side, then the assertions are quite simple, just shaped like this. And for the general case, by noticing that on the right-hand side, GI prime and LJ prime are the products of the elements in the left-hand side, we can use P and Q equals P and PQ to reformulate the left-hand side of VC and reduce to case 1 and find the correspondence of phases. And we provide a theorem to guarantee that. When handling common QEC programs, this is typically the scenario we encounter, since Pauli errors will not change the Pauli expressions, but only alternate the phases. However, we hope that the logic we design can be applied to broader scenarios, including non-Clifford gates, which leads to some non-commuting terms between both sides of the verification condition. When there exists such non-commuting terms, we provide a heuristic to help eliminate the terms in the right-hand side, which do not commute with terms in the left-hand side, by utilizing the fact that P and Q and P and neg Q equals P for commuting PQ operators. And now we can return to the example of the Stinney code to illustrate how our verification framework can be applied to verify its programs. We can write down a correctness formula for the precondition initialized in the logical state plus or logical state minus, indicated by a Boolean B, indicated by a phase of Boolean B. Okay, so in the left-hand side, the first constraint limits the total number of errors, including the errors occurring after this logical operation and the propagated errors. And the second term and the right-hand side indicates the expected logical state. And we divided the program into several segments and provide the precondition derived as the derivation passes through each segment. So the Q0 through Q3. And we will skip these detailed parts. And for more details, you can refer to our paper. So combining the precondition in the whole triple and the one we obtain by derivation, we generate the following precondition. Here, actually, no stabilizer changes. So immediately, we obtain the equivalent classical logical formula like this. So that can be verified using the SMT solvers. Okay, and in the last part, I will introduce the tools we implement for efficient verification of QEC programs. This figure briefly summarizes the overall structure of the verification framework. We first formalize our theory in a cock-proof assistant based on the library coq. And another automated verifier, VeriQEC, is developed in Python, and we demonstrate its efficiency and the functionality by performing different verification tasks. Okay, and both modules of the tool has been made open source. Okay, in a verified QEC verifier in coq, we formalize the semantics of the CQ programming language and prove the soundness of the proof system using about 4,700 lines of coq code based on a coq. We apply this verifier to prove the correctness of a parameterized repetition code program, where the number of qubits in the code distance is parameterized as 2k plus 1 for any positive integer k. And based on the guarantees of the proof system, we implement an automated verifier for QEC programs in Python named VeriQEC. It accepts The user provided information includes the program implementation, the code info, and some simple constraint on errors, and then generate the correctness formula and pass it to AST. Then apply the series to generate the verification condition, further simplified into a classical assertion. And at last, an external SMT solver is invoked to solve the encoded logic formula. And we first enumerate parts of the variables and then parallelize the subtasks generated by enumeration to provide speed up to the solver. Okay, so the evaluation shows that VeriQC could do full verification on service code with 121 qubits, distance that equal 11, within approximately 3.5 hours, thanks to the acceleration. And we further allow users to add some constraints to errors, such as discreteness constraint, which set the maximum limit for the number of errors in each region, and thus lifting the scale to about 360 qubits. And we provide a benchmark of 14 verified QC codes. We select the representative QC code from each code family, like QRD-PC code or such as QRD-PC codes, service codes, and can very hard codes we can implement for tolerant logical T-gate with low overhead. Okay. And at last, we provide a comparison regarding functionalities of the verification tools for QC programs. We summarized the functionalities and scenarios covered by these tools in the table. Okay. At last, let's talk about the future directions and takeaway messages. The first, the completeness issues of proof system is still open problem. And second, this verification framework has the potential to verify certain fault-tolerant protocols. And finally, incorporating SMT solvers into proof assistance to make an automated and verified verifier may also be a direction that is worth exploring. Okay. The last takeaway message is that quantum Hall logic can indeed be practical with concrete assertion languages. And that's all for today's talk. If you are interested in our work, please don't forget to try VeriQC yourselves and discover interesting features. Thanks for listening, and questions are welcome.
All right, we have time for a few quick questions. So, well, I'm going to jump in first. So it's interesting that you built two different tools, a Coq tool and a Python tool. Did you try using like Coq SMT or some SMT integration into Coq and see whether that could give you similar performance, or was there some other obstacle?
Yeah, in the development period, we didn't consider incorporating SMT solvers and Coq together for example, using tools like Microsoft F-star. But after the review procedure, we find that it is possible to incorporate the SMT solver into Coq, and we are currently exploring this direction, and this is listed as the future work.
Okay,
yeah.
Cool. We have a question in the back.
Hi, I'm Christine Riscala from the University of Melbourne.
Okay.
Thank you for your talk. I was curious also about SMT and ROC. So if you've formalized stuff in ROC, it's a little bit unclear to me what's verified in ROC versus what's proven using SMT solvers.
Okay, it seems a little bit unclear to me. So is the tool you mentioned a proof system which incorporates SMT solver?
The Coq theorem prover?
Yeah.
Yeah, versus SMT solvers. Like, what's the
Okay.
What's been done in each of these?
Okay. In my opinion, and in the experiments we have conducted, we find that the Coq proof system is great at verifying some parameterized programs. But the question lies in that in the QC programs, you have to call the decoders, which is a classical, which is indeed some classical algorithms. For example, the Blossom algorithm, for decoding for MWPUN decoders. And the main obstacle here is to explicitly write down the form of decoders for the cockproof system. So for this reason, we only verified the parameterized repetition code programs, with which we can explicitly write down the form of decoders. Okay, so and in the automated verifier, we use SMT solvers and provide constraints instead of the explicit form of decoders. Okay, and that's the reason why we choose to use the SMT solvers instead of the directly employ the cockproof assistant. Yeah.
Okay, let's thank our speaker again. And thanks to all of our speakers in the session and everyone who asked great questions. Yes, please clap. And now enjoy lunch.
Hello? Hello? Testing. Testing.
Righty.
So I'll give you a hand signal when 5 minutes left.
Yes.
It's up to you how much of that time you want to leave for questions.
Hello, everyone. I'm Chris Casangino from Jane Street. I'm delighted to welcome you to this afternoon's session on language design. We've got 3 excellent-looking talks. I'm excited to hear them. I hope you are too. The first of which will be a talk about tree borrows from Nevin Villani.
Thanks for the introduction. Hello, I'm Nevin. I'm here to talk about trees, about Rust, and optimizations. Here's a Rust function, writeBoth, that takes as input 2 references x and y. It writes 13 to x, it writes 20 to y, and then it returns the null value of x. If we look at the type annotations of this function, we find the information that x and y are mutable references. And in Rust, a guarantee of the type system is that mutable references point to disjoint memory from each other. Therefore, when we write to y, we can be confident that the value behind x is not modified in the process. So if we know the value that is stored in x, we can propagate it through and reason that this function always returns 13. All of this is only local reasoning based on type information, so the compiler has access to all of this reasoning. And in fact, the compiler will apply this optimization and replace the load of x with a constant 13, making the function more efficient. Now remember that the correctness of this optimization relies on the disjointness of x and y. So how does that work? Well, there's a part of the Rust type checker that's called the borrow checker, whose job is to ensure that aliasing and mutability are not in conflict. That when you have a mutable reference, there are no other pointers to the same data. And that when you have references that alias with each other, you cannot mutate through any of them. That's quite a strict requirement, and sometimes it's too strict for low-level applications. For these purposes, Rust offers a mechanism called unsafe, which gives the programmer access to unchecked operations, which is effectively a way to temporarily bypass the type system. There's of course a trade-off here. If you bypass the type system, you lose the guarantees provided by the type system. So in Rust, the type system is quite strong. It provides very strong assumptions that no pointer is null. You cannot access uninitialized memory. There are no data races at compile time. You can guarantee that. If you bypass the type system using unsafe, you lose those guarantees, and it becomes your job as a programmer to enforce those manually. If you fail to uphold those guarantees, your code will trigger undefined behavior, which gives the compiler license to do whatever it wants with your code. So how is that relevant to our specific optimization here? Here we have the same function as earlier, writeBoth, and it's being invoked in a context where x and y, its 2 parameters, are created using unsafe, pointing to the same data. We are explicitly using unchecked operations to violate the assumption of disjointness of mutable references. This is observable in the return value of the function. We reasoned earlier that this function always returns 13 under assumption of disjointness, and here it is returning 20. If the compiler applies the earlier optimization, it will change the observable behavior of the program. So here we see a tension between unsafe code's ability to manipulate arbitrary memory and the compiler's desire to apply powerful optimizations. This tension is because unsafe code can break the very assumptions that optimizations rely on for correctness. The way to resolve this is to extend our notion of what UB should be. In addition to the usual causes of UB that are found in many other languages, such as null pointer dereferencing, accessing uninitialized memory, date traces, and so on, we're going to add to Rust a new category of UB, which emerges from aliasing violations. Tree borrows is in charge of defining precisely what the aliasing rules are and when UB occurs. And what this does is it gives the compiler the license to assume that UB does not occur and therefore exploit that to apply powerful optimizations. There's a delicate balance here that must be found because the more UB we add to the language, the more powerful our assumptions, the more powerful the optimizations we can apply. But at the same time, it becomes more difficult to write code that is correct and free of UB. Some people here may find all of this pitch familiar. You may have heard of stacked borrows, perhaps. If not, it's fine, I'll explain quickly. Stacked borrows is the predecessor to tree borrows, and it has the same purpose, to enable optimizations based on aliasing assumptions by declaring that code that misbehaves with respect to those assumptions contains undefined behavior. So, in order to properly introduce tree borrows, I'll start with a brief intuition of what stack borrows does and why it's not entirely satisfactory. So here is a simplified model of stack borrows. The starting observation of stack borrows is that the way the borrow checker works is by enforcing a form of well-bracketedness discipline on all references in safe code. Stack borrows extends this discipline also to unsafe code. So here is an inline version of the program for earlier, where we have an explicit violation of an important aliasing assumption. So we're going to check that stack borrows finds UB here, as we want. A new allocation will result in the creation of a new stack, with the root pointer of the allocation as the bottom of the stack. And the main rule of stack borrows is that to create a pointer from an existing one, you must first ensure that the existing pointer is at the top of the stack, and then you can push the new pointer above. So to create x from PTR, you check that PTR is the top of the stack, and you push x. To create y from PTR, here we find that PTR is not the top of the stack, so we pop until it is, and then we can push y. At the next step, if we try to use x while it is not in the stack, according to the rules of stack borrows, that's a cause for UB. So, just like we wanted, stack borrows here finds UB, the corresponding optimization is enabled. That's great. Stack borrows was implemented in the MIRI interpreter, which is the official tool for detecting UB in Rust, and has been involved in detecting many bugs, including in the standard library. But stack borrows is not perfect. First of all, many people find that stack borrows rules are unintuitive and that its error messages are hard to diagnose. That's not great when we need to write code that is free of UB. Secondly, there are a number of key features of the Rust borrow checker that are not implemented by stack borrows, not modeled. And also, stack borrows is way too strict. To give some concrete number to that, we've analyzed the 30,000 most popular Rust libraries, and we identified over 6,000 individual test cases where stack borrows finds UB. That's a few too much. That makes stack borrow the leading cause of UB in the Rust ecosystem. It means that the model of UB that stack borrows defines is, in some sense, not well aligned with people's intuition of what it should be. So what we want for tree borrows is a model that is overall more permissive while retaining as much of the optimization potential of stack borrows as possible. We find it is possible to have such a model, provided that we replace the stack at the core of stack borrows with a tree instead. To give some sneak peek into how much more permissive we can get the model to be, more than twice as permissive. 54% of the tests that stack borrows finds contain UB are accepted by tree borrows. So we have a much more permissive model. What I'll do now is use one example of a known technical limitation of stack borrows to give you an intuition of why stack borrows is insufficient and how moving to a tree can give us a more fine-grained model. Here is a 3-element array, and stack borrows will view this as 3 independent stacks, one for each location. When we create a pointer to the first element, element 0, it gets added to the corresponding stack. Same thing for element 2. But the stack we're going to be most interested in is the stack at index 1. A common pattern that we find a lot in the ecosystem is that we take a raw pointer, we do some pointer arithmetic, and we use that to access into a different location of an array. If we try to do that in stack borrows, and if the corresponding pointer x0 is not in the stack at index 1, this will trigger undefined behavior. So in order to accept this code, we would need x0 to be in that stack. Now that's not the only possible scenario that could occur. What if instead we took x2 and offset it into index 1? Now UB occurs if x2 is not in the stack at index 1. So we would also need x2 in the stack at index 1. We can't tell in advance which one of these two scenarios might occur, and stack borrows forces us to choose a complete ordering of all pointers up front. What we would really like is the ability to have both pointers side by side, but we can't have that within the constraints of a stack. Already we can see some form of tree structure that emerges. So let's start over, finally, with trees. A new allocation will produce a new tree with the root pointer of the allocation as the root node of the tree. And the main rule of creating new pointers in tree borrows is that you insert them in the tree as a child of the pointer that they were created from. So x0 is a child of root, x2 is also a child of root, and finally we have the ability to represent them side by side. An additional piece of data that we're going to store in the tree is a per location permission. This tells us what are the locations that we're allowed to access with each pointer. Quite naturally, root has the permission to access the entire allocation. In this particular example, x0 has claimed access to index 0, x2 has claimed access to index 2, and the permission to index 1 is still up for grabs. No one has written to index 1 yet. We have a permission that means we have not yet decided which of these pointers is going to be granted access to this location. This choice is going to be made when we have more information. So in the first scenario, x0 accesses into index 1, we give x0 the corresponding permission, and we kill x2 at index 1, ensuring some form of uniqueness is preserved. In the opposite scenario, we do the reverse. We give x2 the permission and remove and take it away from x0. So this is an example where tree borrows is capable of accepting both scenarios. Stack borrows rejected both. So here we have a case where tree borrows is much more permissive than stack borrows. Of course, that's only useful if tree borrows is still capable of finding a necessary baseline of UB. So let's check that tree borrows is still capable of declaring code obviously misbehaving as UB. This is again the same example as earlier, where we have an obvious violation of disjointness of mutable references. And here it is through the lens of tree borrows. Root is a new allocation, PTR is a child of root, X and Y are two children of PTR, and we have not yet chosen which one of these pointers is going to be granted access to the data. When X is written to, Y loses the permission, and when we try to attempt, when we attempt to write to Y, this causes UB. Success. Tree borrows can indeed declare that this code contains undefined behavior. You may notice that compared to the case of stack borrows, here UB triggers one line later. This is an artifact of the fact that tree borrows is more permissive. It leaves the program a bit more room before it declares a violation of the aliasing rules. So I've shown an example where tree borrows is more permissive, an example where tree borrows is still capable of finding a baseline of undefined behavior when necessary. All that's left is to do a more systematic review. The first axis along which we've evaluated tree borrows is there sufficient UB that important optimizations are possible? We have formalized tree borrows in the ROC proof assistant on top of the Simul-Iris framework. And we've proven correct a number of building blocks for optimizations under the assumptions of tree borrows. In particular, the optimization that I've used as an example since the beginning, we can prove that correct in ROC. On the other side, we must ensure that tree borrows is permissive enough that code that people naturally tend to write is allowed. I've already given away the final result of this one. Tree borrows is more than twice as permissive as stack borrows, and the number of regressions is negligible. These results have been confirmed by an independent study. A different team working on FFI found that tree borrows accepts more real-world programs that call foreign functions than stack borrows, and that this is in part due to how tree borrows handles pointer arithmetic. If you'd like to try out tree borrows for yourself, tree borrows is officially shipped with Miri, so you can either run that on your machine, or even easier, upload your code to the Rust playground and try it on there. See if your code contains undefined behavior. If you'd like to learn more about the technical details that I've skipped over, we have plenty of additional reading material, or you can ask any questions and we'll be happy to answer either right now or later. And finally, if you're interested in this kind of research, there are postdoc positions available at MPI and at ETH. Thank you for your attention.
We have plenty of time for questions. There's a microphone up front here if you want to come to the microphone to ask them.
Marissa from University of Utah. Thanks for the great talk. What's the impact on type checking speed?
Okay, so note that tree borrows is not inside the Rust type checker. It's in an external checking tool, so it does not affect the type checking at all.
So what is the impact on the stack borrow? What's the speed like?
So in Miri, tree borrows is a bit slower than stack borrows. Miri is already much slower than compiled code. It's not used for applications where speed is actually a concern. So we consider that the slowdown is not a significant downside, but there are always improvements that are possible, of course.
Hi, Sasha, Imperial College. Do you have a plan for the leftover 30K tests that don't pass? How many of those you think are real undefined behavior that should not be eliminated as test failures, and how many do you think?
So you mean the 3K?
Yeah, 3K, sorry.
Yeah, so there are 6K stack borrows violations, 3K tree borrows violations. I guess I could contextualize that with how many violations of other kinds of UB there are. So stack borrows is the leading cause of UB by quite a bit, because the second one, I believe, is uninitialized memory is around 2.5K. Bad deallocation is around 3K. There's another one I forget. Help me here. That's fine. So whatever. This brings tree borrows in line with other kinds of UB, where stack borrows was far more prevalent than them.
Cool, thank you.
Hi, Jakub Pachurski, University of Cambridge. I have more of a clarification question. I also see the comment in the red box.
Yep.
And what I start wondering is, so stack borrows and tree borrows are sort of supposed to be approximations of undefined behavior, and then there's an actual point which says what is undefined behavior. So could you just put this on a spectrum and say how those three things relate? And like in terms of what is safe approximations and unsafe approximations? Because this seems to imply that this might become an unsafe approximation, and that's a bit surprising.
So stack borrows and tree borrows both try to be the defining model of aliasing UB.
Okay.
What they should be approximations of is the actual UB that is currently being exploited by the compiler.
Yeah.
There is no other model that proposes aliasing UB for Rust. So if one of stack borrows or tree borrows is stabilized, they will become the definition of UB, not an approximation of the UB.
Okay, so this is specific. So code that is accepted by tree borrows may be declared unsafe. So it's possible that this will be standardized to be stack borrows, but right now it's both are safe. Both like detect all the aliasing.
Currently, it's recommended to be compliant with stack borrows, just in case a model that's more strict than tree borrows is stabilized.
Yeah.
But stack borrows as it is basically guaranteed to never become the standard. Way too many people would complain about that.
Okay, thank you, that clarifies it. Thank you.
I think one more question while our next speaker gets set up. Dan, if you want to start. Thank you.
Sure. Jonathan Aldrich, Carnegie Mellon University, and one of the co-authors on the ICSI study that you mentioned.
Excellent.
So I just wanted to say thank you for sharing your work, which is amazing, before publication, so that we were able to build on it. I think it's a great win for open science.
Thank you.
All right, let's thank our speaker again.
Try again.
Yay. Okay, let me see. Great. Hi, everyone. Thank you for attending the talk. This is Principal Type Inference under a Prefix, a fresh look at static overloading. And I'm Dan Lyon from Microsoft, and this is joint work with Wenya Ye at the University of Singapore. And also I want to thank the following people. Tim Whiting is a PhD student in Utah, and his work that I'm doing with him on implicit parameters really inspired this. Sam Lindley helped a lot with early feedback, and there's an anonymous reviewer who I hope to meet here, who I really would like to thank, because his feedback or her feedback really improved the paper significantly, and I'm very thankful for that. Thank you. So in a nutshell, the work I'm presenting today is like a new set of type rules called HMQ. And I would say a better set of type rules than Hindley-Milner, but maybe that's too courageous, right? So let's say it's a more algorithmic set of type rules than Hindley-Milner. And usually that's bad, but I would argue that the clarity of these rules is still very close to Hindley-Milner, which is a very good thing. But there's a special property that every type you derive is actually principal. There's no choice in the types you're deriving. And that in itself gives a really big advantage if you want to define extensions to Hindley-Milner. And in practice, it turned out that many extensions like impredicative type inference or static overloading that I'm going to show, and lots of other things, they're really hard because we want to put it in the Hindley-Milner rules. But if you use a slightly more restrictive set of rules, the HMQ that I'm proposing, I think it's much easier suddenly. So I'm kind of hoping that HMQ will be a new basis for specifying many type system extensions in practice. So to make this argument, I'm going to first explain Hindley-Milner to you. Let me see. All right. So we have expressions with lambdas in there, and we have monotypes, and we have polymorphic type schemes. And then in Hindley-Milner, the most, or Damas Hindley-Milner, the most important rule, I would guess, is like the lambda rule. And there it's a little special because the tau 1 we see here, well, we can guess any type for that. So it's a very liberal system, Hindley-Milner. So for example, if I have lambda x dot x, I could, for example, guess that x is an int, and then I derive int to int for the expression. But I could also guess that it's a Boolean, and then I can derive that lambda x dot x is bool to bool. So this is, of course, well known to everyone. And then Hindley-Milner has also something called principal types, so you can do generalization and instantiation. So if I do again lambda x dot x, one thing I could also guess is like some abstract type alpha, and then generalize it. And then, we get for all alpha that alpha, and this is the best type, right? So Hindley-Milner always has bestest types, and that's a very good property, right? And, well, to top it off, what a great paper, by the way. They also have an algorithm that computes this bestest type, right? Algorithm W. And I'm not going to go into it, but I'm going to highlight some things about W. So one of them is it threads a substitution through each derivation, which makes it actually hard to reason about, right? That's why we like the rules and not kind of the algorithm in general. And you can also see it actually never guesses a type. It always uses fresh type variables for these tau 1s in the function rule. And finally, in the applications, it uses unification. This gives rise to the substitutions, right? It matches the argument and parameter types. Yeah, fantastic paper, by the way, from 1985. It's still fun to read. It's only 12 pages, and it has everything. And yeah, and this is, I would say, this is kind of the beauty and bane of Hindley-Milner. So Hindley-Milner is like this beautiful rose in the sunlight because we have these beautiful logical rules and a algorithm that actually computes always the best type. So it's just really great, right? But as soon as you want to extend it, there's lots of thorns around this beautiful rose. And that's kind of because of this guessing and this liberal nature of the rules. If you want to do certain extensions, that can really get in the way. And I would argue that in many previous work, there's lots of artificial constraints that are not really essential, right? It's just kind of to keep Hindley-Milner in check. And that's what we try to address in this work. So I'm going to give some two examples of how how extensions can lead to kind of funky restraints and make it more difficult. So the first one is from my favorite language called Coca. Ask me about it after the talk. And one of the things we try to do there is say, hey, maybe we can do static overloading. What does that mean, right? So maybe I have like two functions, my show, and in Coca you can locally qualify them as if they're in a mini module. So I have here an int my show that works on integers, and bool my show that works on booleans. And then I would like to use them. And I would love it if the compiler can help me elaborate like which module I mean, right? So in this my show x, my show true, I would love to elaborate to int my show and bool my show. So that's, I think, the essence of static overloading, like you see in C, for example, too, right? And I want to reject things too if I don't know it. Like the bottom one, like wrong x, I have no idea what the type of x is. Well, then I want the compiler to complain. I have to manually write the full qualified name because I can't tell. So suppose I want to formalize this in Hindley-Milner, I quickly get into trouble because of this guessing of the types. So for example, if you look at the last one that I want to reject, like the wrong x, it's like lambda x dot my show x. So here it is, lambda x, my show x. Well, maybe if I indeed guess an abstract type alpha, I would reject it because I can't tell, right, what my show I want to use. But unfortunately, in the standard Hindley-Milner rules, I could also guess int for this parameter x, and then I could say, well, that must be the int my show. Or maybe I guess a bool, and then it would be a bool my show. And now I'm losing principal types, right? One is rejected, and I have two other ones that I could elaborate to. And it turns out that it's really hard to formalize it in a nice way, that you don't want these bottom ones, and you kind of always want to reject this example. And for example, boxy types is one example of that, because I don't know if people are familiar with it, but the kind of fun work by Dimitrios Vitiniotis and Stephanie Weyrich and Simon Payne-Jones, they had these boxy types where that would kind of be information you cannot see, right? And that could be used here to do this kind of thing where the int and the bool would be inside a box. But I mean, the lesson is it's really complicated. You get a very different kind of type system rules suddenly. I'll give another example where Hindley-Milner kind of gets in the way, or the liberal nature of it. Well, I wanted to say, side note, algorithm W has no problem here. So the rules are tricky, they're very liberal, but the actual inference algorithms would be fine here, because the inference algorithm always uses the abstract type. It will never guess like int or bool, right? So there's something there that's kind of important, that the algorithm would be easy to do static overloading. It's just in the rules. So another example of this is in predicative type inference. It's like a hobby of mine. Since 2004, when there was a beautiful thesis by Didier Le Baudelin and under Didier Rémy, and they made this MLF system to do impredicative type inference, and that's where the idea of prefixes actually comes from. But they have lots of stuff, like flexible bounds and stuff, and then in 2006, there's more work, the boxy types at ICFP, and they had this new idea of boxes around types, and it was later followed by another paper which also uses boxy types. And then I wrote a paper too, HMF, and it used, oh my god, polymorphic weights to do the same thing. And there's more, like recently there's FreezeML by Sam Lindley, Frank Emmerich, and others. And they have frozen types, I guess you could say. And in the same conference, there was also the quick look paper, which has like quick look rules, and all of them do impredicative type inference, but it's unclear which is best, right? So we can't really compare these systems because they all have their own special flavors to constrain Hindley-Milner. And it's unfortunate, right? So the only way we can gain insight which one does what by having like lists of difficult functions, and then say like, oh, this system checks this, but it doesn't do that one, but that system does, etc. So I'm hoping HMQ can help there as well, and I give an example of two of them, like HMF and FreezeML. So in FreezeML, there's a let rule, looks like this, and it has this funny principal condition. And it says, well, for all derivations, you should pick the best type. And that's a really not so nice constraint in a logical type system. Like, it's not really an inductive rule. It's almost impredicative by itself, because above it could be the same condition. And then you want to suddenly have to reason with all of them. And actually, the thesis of Frank is like, you see that the proofs are really complicated just by this extra condition, right? So you have to do a lot of extra work to show things are correct. And just to show, I'm not like being, talking down on FreezeML. I will talk down just as much on my own system because it has the same kind of bad side conditions. So HMF has also a constraint that says, oh, for all derivations above it, pick the best one, or even here, like pick the one with the least polymorphic weight. Well, what is that even, right? So you get these funny constraints just to keep Hindley-Milner in check. And again, if you actually look at the algorithms that implement FreezeML or HMF, it's not so hard. They're actually small deviations from algorithm W, and they don't contain any of that complexity. So maybe we've been doing that wrong, right, over the past decades. We have these beautiful Hindley-Milner rules and this great algorithm W, but as soon as you want to extend it, we get not so beautiful rules with lots of funny stuff. Boxy types, wobbly types, frozen types, polymorphic weight, well, all kinds of things. So maybe instead of going all the way we should maybe be happy with some handsome HMQ rules, right? Like, maybe not as beautiful, this rose, but at least there's no thorns, right? It's like me, it's special in its own way. Right, so that's the rules I'm going to show now. Type in front under a prefix, and I argue the clarity of Hindley-Milner, but it's easier to extend, right? And because you always derive principal types, we don't need any side condition in FreezeML. It will just work. And because we don't do any guessing, static overloading will also just work. You don't need any extra constraints. And the hope is, of course, users can then reason more easily about which program is accepted, because like easy rules. And the compiler writers can still write good and sound algorithms. I'm going to hurry a bit. So these are the rules. I hope you think they're also simple enough. And of course, Simon Peyton-Jones always says, don't show type rules, but now I'm doing it anyway, so I hope it won't be too bad. I just want to say there's still an environment as input, but now you get back a type and a prefix Q. And you can see that there's no more guessing. Like the type for a lambda is always like an abstract type variable, a fresh variable. And just like algorithm W, we kind of explicitly show equivalence between types, like unification, in the application role. And finally, there's just a tiny local condition on the let that says that all the free type variable in sigma must be in the gamma. And that ensures that those types are always the best types at the let bindings. And there's no, for all derivation stuff going on. Wow, okay, I'm going to hurry a bit. So here's, for example, how you derive the identity function in HMQ. So you always guess a fresh type. So there's no more guessing, sorry. You always pick a fresh type, no guessing. And in the end, you can only derive this type. You always get for all a dot a for lambda x dot x. No choice at all. So you can't derive into int or bool to bool. Of course, that gives the question, well, how would you check lambda x increment of x, right? How do I get into int if I have to always pick a fresh alpha, like some abstract type for x? And that's where the prefix is needed. So these prefixes are just kind of little constraint sets in a special form. They're just, type variable equals a monotype. And you can have duplicate bindings, like alpha is bool, alpha is int. They can even contradict each other. But if they're solvable with a substitution, then it's also implementable with a substitution. And that's one thing the paper shows. And the nice thing is we write very concisely, like Q1, comma Q2 to compose them. And that's just the union of the two prefixes, but they must be solvable. And this gives a very concise way to write your type rules, and kind of knowing like, we know how to implement this using, substitutions or like very fancy techniques. And we know that works out, but it gives you a very good way. It kind of abstracts away from the implementation of a substitution and makes it really easy to specify the rules. Yes, oh man, I will never get to the end of the talk. Okay. So here's an example of that compositional style. Here's the rules for unification, like what types are equivalent. Again, two types come in and a prefix comes out. And you can see that if you use this comma, you can just say, just combine the constraints, the prefixes you've collected in the subderivations. And that's really, really nice for specifying clean rules. And then you can easily derive, for example, here that alpha to beta is equivalent to int if under a prefix that is alpha is int and beta is int. And interestingly, I'm going to skip that. The only place where you can get this constraint is in the var rule. And in all other leaf nodes, it's always empty. And because they come down, you cannot invent new constraints. It's kind of like linear types. You have to get all your resources together. I'm going to skip through it. Otherwise, I would love people to have an opportunity to ask questions. And you can look in the paper to see how you do applications. But an important part is this gen sub rule, which allows you to substitute back these constraints and the prefix into the types. And then if the inc x, you can actually substitute the alpha and beta, and then you get into int out. And it has very good properties. And in the paper I show you, you can actually HMF and FreezeML, you no longer need this funny constraint because it's already satisfied. And with HMF, with the first class polymorphism, you can also show, you don't need it anymore. It's just a simple match. And then we also show static type, static overloading. In this case, you have bidirectional rules. You push down the type. But again, because it will always be the same type, never guessed. So we can just resolve it, right, if possible. So it's almost so simple now that it puts us out of work. Like, how can we write papers if that works so well? Yeah, and that's the end of the talk. Thank you so much for listening, and maybe try it out for your own language in the future.
We have time for a few questions.
Looks like really cool work. So as someone who's read those zoo of papers a long time ago, I have to ask, what's like the poster child example of something you can handle that the previous papers couldn't handle, or vice versa?
The poster child, wow, yeah. It's hard to say. I think there's more that still has to be explored. But for example, if I look at the boxy type paper, I can see that these boxes are really those abstract types that I introduce, and that what's in the box is what would be in the prefix in this system. So I feel like we could rephrase that one as well, and probably the others too. But since, right, like you know, they're all complex, it would require work, right?
Okay, and just to be clear, you mentioned two of them a few slides
HMF
earlier.
and FreezeML.
So did you actually prove some kind of formal correspondence with them?
No, so in the paper I show how it's done, but I don't show it formally. So there's no proof that what I do is actually, right, HMF. That's yes.
Okay, thanks.
Thank you.
Okay, I'll ask a question while our next speaker gets set up. Dan, practical implementations of type inference don't implement exactly algorithm W. They often use like levels or something. Is that approach compatible with this somehow? Or,
yes, it should be. Right. So yeah, algorithm W can be used unchanged. So that's a really good thing. And so you could use your in-place updating graph right to do HMQ as well. Right. Thank you.
Cool. Let's thank Dan again. Our last speaker will be Mako Bates, who's going to tell us about choreographic programming.
Hello, I'm Mako Bates. I'm here to tell you about choreographic programming that is efficient in terms of its communication overhead, that's portable in the sense that you can use these techniques in your favorite language, and that is census polymorphic, which is a property that I'll get to in the second half of my time. So I'm going to spend a few minutes setting the stage, making sure we know what choreographic programming is and why we want it, and how other people have worked on that idea. And then I'll explain conclaves and multiply located values, which are our solution to one of the fundamental problems in choreographic programming. Then we'll talk some about our implementation strategy, how that interacts with conclaves and multiply located values. And finally, we'll get to census polymorphism, which is one of the keys to allowing real code reuse in choreographic software. So writing systems of concurrently executing programs is hard. We've got 3 small programs up here that are designed to run simultaneously and in communication with each other. And we need to ask questions like, what does this system of programs do? How might it fail? Does it do what it does efficiently? We can make reasoning about systems like this easier for ourselves by instead writing just one program that describes everybody's behavior simultaneously. That's the idea of multi-party programming, the particular flavor of which that we're talking about today is choreographic programming. In choreographic programming, you write one protocol from a third-person omniscient perspective. It's exactly like you're telling a traditional Alice and Bob story. Characteristically, we don't have distinct send and receive operations. Those are 2 sides of the same coin. We call that unified operation communicate. We write it often with a little squiggle arrow. So on the left here, we say Alice communicates X to Bob, who binds it as Y. During compilation or at some other point in the process, you're going to do endpoint projection, which is where you extract an individual party's behavior and an implementation of their behavior from the global choreography. So on the right, we have the projections to Alice and to Bob, respectively, of this one communication operation. For Alice, that projects as send X to Bob. For Bob, it projects as receive Y from Alice. The advantage of writing your software this way is you get some static safety guarantees. You'll never have to worry about deadlocks. And when a party receives a communication, they don't need to worry about where in the program the sender was when they sent it. So it's an easy way to write your software. It makes it easier to reason about. Here is a more involved pseudocode example that shows off those same features. We've got one thread of action in which 3 different parties are taking actions at different times. On line 4, we see that unified communication operator with the squiggly arrow again. On line 2, the argument this function requests is a list of requests located at the client. And something very similar happens implicitly on line 8. The type checker or the compiler or somebody is going to have to infer that handle R double prime is something that's done by the processor. So this is pseudocode. Our goal is to write actual software like this. There are some existing systems you can use. So Coral is very nice. It is tightly integrated with the Java ecosystem. Pirouette has a similar level of integration with Coq. Those are expressive and efficient, but they need their own compilers. If you write your software in Coral, you'll have some Java code in there, but you have to use the Coral compiler. There are also some intermediate systems. So Corex and Chlore augment their host language's syntax with macros and compiler plugins, But what we want is fully library-level choreographic programming. And Hascore showed that that was possible at ICFP a couple of years ago. It's very easy to use. You start a new Haskell project, you import Hascore, and you write your choreography. What you lose is the efficient and explicit communication that ought to be characteristic of choreographic programming. The reason why this is hard, the thing about the choreographic programming that's not trivial, is managing knowledge of choice. So in this diagram, we're supposing that Alice has some located Boolean called x, and Bob's behavior needs to depend on that x. So when Alice looks at x and chooses which of these branches to take, Bob needs to know that choice and take the same branch. And right away, we have to ask, does anyone else need to know? In this particular case, yeah, actually everyone needs to know, because if we imagine projection to some third party, such as Carol, then they need to have either receive an integer from Bob or receive a string from Bob, and that needs to be well defined. Coral and a lot of prior systems use a select and merge strategy in which there's a designated communication operator just for managing knowledge of choice. And if the user makes any mistakes in their knowledge of choice management, that's detected during endpoint projection. But if you're doing library-level choreographic programming as a fully embedded DSL, then your endpoint projection is going to happen at runtime. And we don't want runtime errors. So Hascore's strategy was to implicitly broadcast the guard of every conditional to everyone, which works, but it's not efficient because not everybody needs every single guard. The first step towards improving on this is to take a census of the participants. So the census is what we're calling the list of parties who are present to participate in a choreography or in some part of a choreography. Some prior works have had these as part of their type system and use them to manage function declaration and function application. Our formalism, lambda c, also annotates case expressions with their own censuses because it's using the census as part of the knowledge of choice management strategy. Here's what effect that has on a broadcast situation. We go into the conclave with Alice and Bob, so the census is now just Alice and Bob. When Alice broadcasts X, well, actually, she's just sending it to Bob. Carol's not inside the conclave, she doesn't get it. And here's how we use conclaves and broadcasts to do efficient knowledge of choice. On line 3, our census is explicitly client, server, and backup. The first thing that happens is on line 5, client sends request to the server. And then down on line 8, we're going to want to branch on the nature of the request. Is it a get or is it a put? But only the server and the backup need to be participating in that branching operation. So on line 6, they enter a conclave. That entire do block that starts on line 6, the census is just server and backup. So on line 7, when we broadcast the request, that doesn't go back to the client. They don't need it. They're going to skip this whole block. And then the server and the backup can branch on line 8 as described. But what do we actually get when we leave the conclave? What is the type on line 6 of the bound variable response? In our earliest versions of Chorus, we just required that conclaves return multiply located values. The details of that turned out to be buggy, and also we can do better than that. I got to skip over some of the story of exactly why, but a conclave has to return a multiply located value. Specifically, the conclave operator takes a choreography with some census and lifts it to a choreography with a super census, and it wraps the return value as a multiply located value owned by the subcensus. We've seen a couple instances of located values so far. They're just values or variables annotated with an owner. Multiply located values work the same way, but they have a list of owners. The critical thing about a multiply located value is that there's only one value. All of the owners know and agree on that one value. So this gets us back the efficiency and explicit communication that we hope for in choreographic programming. Expanding on the earlier diagram, we assume that Alice owns some X. Inside the conclave, she can broadcast it, so now she and Bob both have it. They can branch on that together, and whatever the return value of this conclave is, outside the conclave will be viewed as a multiply located value known to everyone who was in the conclave, Alice and Bob. Carol never participates in that. So our formalism combines multiply located values and conclaves to make an efficient and intuitive and also completely type-directed knowledge of choice strategy. It's a lambda calculus. It has normal properties for lambda calculus like preservation and progress. And endpoint projection is well-defined and sound and complete for all well-typed programs. So your network semantics never get stuck. We get some other stuff from multiply located values. We can reuse knowledge of choice in sequential conditional blocks. And we also get really concise expression of active replication. But finally, this is really easy to implement. Let's talk about implementation strategies. In a sense, choreographies are just another DSL. Where the rubber hits the road is endpoint projection. Hascore did this with monadic effect handlers, but you don't need that. You don't even need monads. Any form of dependency injection should suffice. What we're doing is we say, choreographic programming with such and such census, that's an interface. A particular choreography is a consumer of that interface. And you do endpoint projection by providing an implementation of the interface that implements the specified party's behavior and skips over everybody else's actions. There'll be some core operations kind of at the foundation of that interface. You're not set in stone exactly what those are, but I do recommend these as a good choice for your 4 foundational operators. We've talked about broadcast and conclave. Congruently explicitly does active replication. There's a couple different options for how to do it, but you'll want to have some way of doing that. And locally handles side effectful computation by one party at a time. In multi-core, we're using freer monads. In Chorus, we're using traits, the trait system. In Choreo-TS, we're using polymorphism in a fairly straightforward way. If your language can do dependency injection in whatever form, you can probably do choreographic programming. And insofar as your language can do type-safe dependency injection, you can probably do type-safe choreographic programming. But other than intuitive and efficient knowledge of choice management that's statically checked by the host language's type checker with recyclable embodiment of knowledge of choice as data, what do these techniques get us? Well, obviously they get us everything that the host language gives us. This is real, compilable, executable Haskell written using the multi-core library. And it contains a bunch of stuff that I didn't have to build. We've got monadic bind, lambda case, do notation. We've got Haskell's clear distinction between pure and impure code. I got all that for free. And there's a few other functions in here that I haven't described yet. On line 11, the gather function, and parallel on line 9. The second argument to this function on line 4 is a faceted value. These are also things that we get, quote unquote, for free in Haskell. And they're really important because they're what's doing census polymorphism in this example. So let's talk about that. Modern concurrent protocols have lots of participants. I found some examples where they're running them with thousands of participants. And really, once you get up to 4 or 5, you don't want to have to rewrite your software every time somebody wants to add one more participant. So looking at the sequence diagram here, there might be thousands of servers, or it might be the case that there's only the one server called primary. This diagram is ambiguous about that, and that's exactly how you actually write it in multi-core. We have the traditional concurrent programming operators scatter and gather, and then a third one, parallel, is how you do handle request in the middle of this diagram. In order to give those things sensible types, we need some new data types. So faceted values are very much like multiply located values. They accept that their contents diverge. Every owner of a faceted value will have their own value of that value. Quires are static vectors indexed by parties. So the opposite of a faceted value is actually a located quire. And as I mentioned, we get this for free in Haskell. For free in the sense that we could have left it out of the library and people would have been able to write it themselves. Not free in the sense that you'd first have to write this stuff. So the point of this code block is not to learn anything profound by understanding it, but rather that this is a transparent and completely type-safe helper function that rests on top of the core API I was describing earlier. Down at the very bottom, I don't know if everybody can see, we have this type P indexed. That's a party indexed lookup table from type level parties to runtime values. The types of those values depend on the party you're looking up. Sequence P sequences over parties. It takes a P indexed and a P indexed whose values all have a common monadic structure, and it sequences them together in that monad. So this is great. We can do this stuff very nicely in Haskell, but it's too good to leave in Haskell. We got to do this in all the other languages. So in your language of choice, what you'll probably do is you'll add the key operators that you want for census polymorphism as little black boxes in your core API. A lot of languages aren't going to have enough type level hijinks for the sequence P strategy. So in Chorus and Choreo TS, we hard code fan in and fan out. Fan in is a loop function. It takes a body that returns a located value with invariant owners, and it loops over a list of parties and wraps up all those return values as a quire. Fan out is basically the same, except that the body returns variables located at the indexing parties, and they get wrapped up as a faceted. But if your language can't actually encode those, you can do the even more specific operators, scatter, gather, and parallel. You lose a little bit of flexibility in each of these different options, but at this point, we don't actually have a case study showing why you would need the full power of the sequence P system in the real world. So kind of wrapping things up, you can do choreographic programming in whatever language you want, using conclaves and multiple located values with census polymorphism. You won't have to worry about your concurrent systems deadlocking or other kinds of miscommunications. You can handle all kinds of different configurations of participants. In the paper, we've got a couple of case studies. A lot of the details are in the appendix. My next 3 slides are QR codes for each of our implementations. So multi-core is our Haskell implementation. You can pull it off of Hackage right now. There's going to be a version 2. So if you're interested in what might go into that, you can come to my dissertation defense a week from tomorrow. Chorus is our Rust implementation. On crates.io, it's chorus_lib. It has really nice tutorial-style documentation. Choreo TS is our TypeScript implementation. You'll have to install it from GitHub right now. I mentioned that different languages give you different things for free. The thing you get for free in TypeScript is really good type-level expression and handling of subset and membership constraints. So that aspect of the system actually works out much cleaner in Choreo TS than what we were able to do in the other languages. Thank you again, and thank you to my co-authors up here. My name is Mako Bates. I am looking for a job. Don't forget to fight fascism, and we have time for some questions.
I have a question, Mako.
Yeah.
You mentioned that there were several different options for the congruently operator. Can you tell me about some of those?
Yeah, so in all of these systems, we have a really minimalist set of core operations. You could fluff those up a little bit, and that would save you some layering work on top. In the case of congruently, it's kind of a weird odd one out. The obvious other option would be a simple naked or unwrap operator that just takes a multiply located value known to the entire census and turns it into an unlocated value. For version 2 of multi-core, we're going to have an even more bare bones system where the entire notion of a located value kind of disappears. But I don't think we have time for that in this session.
Okay. So on one of your like code snippet slides, I saw that you had like an example with a conclave where you sort of explicitly write down what the census is for that conclave.
Yep.
Are there any ways to sort of automatically synthesize this, or have the compiler tell you that, hey, you've added someone to this census that's like not necessary, or like this is, you know, bigger than it needs to be, or like if for example I explicitly write conclave server backup and client on line 6, is the compiler able to help me out and say client doesn't actually need to be here?
No, it won't. And depending on the kind of performance or other property that you're trying to get out of it, you don't need it to. We could put together a situation where there'd be a performance cost to including people erroneously in the census.
Well, like when you broadcast, you have to send it to everyone in the census, right?
Yeah. So if you're doing a broadcast, in practice, the actual point-to-point communication or multicast is its own conclave with a broadcast that we build them all out of. So broadcast is not, when you're actually writing a choreography, you might not be using broadcast.
I see, okay.
But yeah, that's a good point.
I think we're going to have to take the last question offline just for time, but let's thank Mako again. And that concludes the session. Thank you, everybody.